Hey friend, curl up, slow your breath, and let the noisy day fade. Tonight we'll wander to the edges of thought, where numbers never end, shapes nest inside shapes, and time itself feels like a tide. I'll keep the pace gentle and the stories clear so your curiosity can glow without keeping you awake. If your eyelids get heavy, that's part of the plan. Ready? Let's step into infinity together. Chapter 1. What do we mean by infinity? Infinity is a word that feels familiar until you try to hold it still. People reach for it when they want to say beyond counting, but in mathematics and science, it is not a larger kind of number waiting at the end of a very long road. Infinity is a way of talking about the absence of limit, a way of encoding processes that never finish and collections that cannot be exhausted. That difference matters. If you mistake infinity for a monster number, everything that follows will look like a trick. If you take it as a disciplined way to talk about the unbounded, the puzzles begin to resolve and the usefulness becomes clear. Infinity, in this sense, is not a destination, but a method. Not an object you can pick up, but a framework that lets you reason cleanly about what happens if you keep going. The earliest sustained arguments about the infinite in the West arrive with Greek philosophy. Zeno's puzzles about motion are remembered not because they proved movement impossible, but because they showed how quickly ordinary intuition breaks when endless subdivision enters the picture. In the so-called dichotomy, a runner must first cover half the remaining distance to a finish line, then half of what remains, and so on without end. How can arrival happen if there are infinitely many steps? Today, calculus gives the essential answer. An infinite sequence of ever smaller contributions can sum to a finite time. The point here is not to solve Zeno once and for all. That fuller discussion comes later, but to notice how infinity forces us to refine the language in which motion and change are described. Aristotle drew the moral carefully by separating two senses of the infinite. Potential infinity is an open-ended process. You can always add one more number, always divide a segment again, always take another step. Actual infinity would be a completed totality containing infinitely many items all at once. He accepted the first and rejected the second, a caution that preserved coherence in his system and shaped thought for centuries. The distinction still influences how we talk. Much of modern analysis is written in the grammar of potential infinity. Statements about what happens as a variable grows without bound, about how close you can get to a target if you are allowed to refine your approximation indefinitely, while set theory treats certain infinite collections as actual, completed wholes that can be compared and studied in their own right. Other traditions placed infinity in different lights. Ancient Sanskrit texts speak of the infinite with aphorisms that are poetic and exact in spirit. From the infinite, when the infinite is taken, the infinite remains. The line is not a license for sloppy arithmetic. It is a hint that ordinary subtraction loses its grip when applied to unbounded totalities. Medieval theology attached the word to discussions of perfection. If the divine lacks every limit, then eternity, omniscience, and omnipotence are attributes expressed in the language of infinity. The difficulty that followed was always the same. How can finite language and finite minds describe what has no boundary? The effort to do so left a mark on philosophy, but the mathematical treatment of the unbounded would eventually take a different road. The scientific revolution quietly moved the infinite from the pulpit and the symposium into the workshop. When Newton and Leibniz fashioned calculus, they created a disciplined way to talk about instantaneous tendency and accumulated effect. The modern formulation avoids treating infinitely small quantities as tiny marbles and instead defines limits with the precision of inequalities. To say that a function has a limit at a point is to say that as we push our attention arbitrarily close to that point, the function's values are corralled arbitrarily close to a single number. No single finite stage achieves the limit. The limit is the faithful translation of what would be reached if the refinement never stopped. This is how mathematics turns the vague promise of keep going into a definite value. With limits in hand, mathematics expresses change with clarity. Velocity at an instant, the curvature of a trajectory, the area under a curve, and the accumulation of small influences into a large effect are all described by processes that conceptually continue without end while delivering finite answers. You never need to perform infinitely many steps in time. You need to know what would happen if you kept going. That is the sort of question the calculus answers, and the reliability of its answers underwrites much of modern science. The infinite enters here not as metaphysics, but as a clean way to talk about arbitrarily fine resolution and arbitrarily long addition. For a long time, mathematicians were wary of granting infinity full citizenship as a completed object. The 19th century changed that stance decisively. Georg Cantor developed a theory in which sets, including infinite ones, could be compared by pairing their elements one to one. Two sets share a size or cardinality if such a pairing exists. In the finite case, this agrees with counting. In the infinite case, it produces surprises that are now standard landmarks. The set of whole numbers and the set of even numbers, for example, can be matched perfectly. Each whole number n pairs with 2n, so they have the same cardinality even though one looks like a half of the other. Intuition formed in the finite world treats this as impossible. The formal pairing shows that size works differently for unbounded collections. Cantor's deepest discovery was that not all infinities are equal. The continuum of real numbers, every possible decimal expansion, cannot be listed in a sequence that hits them all. A brief diagonal idea shows why. Given any purported list, you can build a new real number that differs from the first entry in its first digit, from the second in its second, and so on, guaranteeing it is missing from the list. No enumeration can succeed. The conclusion is what matters here. The detailed construction will be taken up later. Infinity, it turns out, comes in endlessly many sizes. Once that vertigo passes, the arithmetic of infinity becomes a field of study rather than a source of contradiction. Adding finitely many elements to a countably infinite set does not change its size. Placing countably many countable sets in sequence still yields a countable set, whereas even a single interval on the real line has uncountable size. None of this is paradox after the definitions are mastered. It is the new normal for unbounded collections. What looks like sleight of hand from the outside is, from the inside, a consistent extension of the idea of size, tailored to the infinite, the way ordinary counting is tailored to the finite. Infinity also changes how mathematics handles completion. Consider a sequence of rational numbers that homes in on a value like the square root of 2, which is not rational. In the world of rationals alone, such a sequence never quite lands. By adjoining all limits of Cauchy sequences, mathematicians build the real numbers, a setting in which every Cauchy sequence converges to a value that remains within the space. The move does not assert that a physical process has executed infinitely many steps. It asserts that the space in which you do analysis has been designed to welcome the limits generated by its own processes. Infinity, in this sense, appears as a kind of closure, a promise that the limits your methods produce will fit inside the framework you are using. Infinity is a careful instrument, but it is also easy to misuse. Treat it as a placeholder for mysteries, and it becomes an incantation. Treat it as a number to be juggled casually, and contradictions appear. The discipline of modern mathematics polices the boundaries. Proofs that invoke infinity are explicit about what is allowed to grow without bound and what is held fixed. When a statement says that a function diverges at a point, the claim is not that a dial on a laboratory instrument will swing to an infinite value. It is that for any bound you name, the function eventually exceeds it as you approach the point. The words sound dramatic, but they have a modest, exact meaning. Because we are finite, our relationship with infinity is colored by psychology as much as by logic. Children grasp that one can always add one before they can recite a definition of an unbounded set. Adults, too, carry habits that are faithful servants in the finite world and unreliable guides in the infinite one. Education in analysis and set theory is partly a process of retraining intuition. You learn to ask which variable is moving and which quantities remain fixed. You learn that for all and there exists do different kinds of work and must not be swapped. You learn to separate the feeling that something should be true from the demonstration that it is. In that sense, infinity is a tutor in intellectual humility. Infinity also lives in culture. Writers and artists return to it because it invites a special kind of wonder. Borges imagined a library containing every possible book within a fixed format, a place where meaning flickers as rarity in a sea of nonsense. The image is fanciful and instructive at once. Given unbounded combinatorial space, almost everything exists, and the problem becomes how to find the parts that matter. Escher drew staircases that climb in loops and tessellations that repeat toward a horizon the eye cannot quite reach, visual parables about patterns that refuse to terminate. These works do not prove theorems, but they sharpen a habit of mind that expects the infinite to bend intuition. There is a quieter benefit to learning how infinity is used well. It refines language. Words like always, never, forever, and almost surely have exact meanings in mathematics that differ from their rhetorical cousins. An identity that holds for all natural numbers holds for each and every one, with no hidden exceptions waiting far along the list. A property that holds eventually holds beyond some stage, and the existence of that stage is part of the claim. The ability to speak that way is not pedantry. It is the way mathematics prevents grand words from doing sloppy work. Computer science adds another complementary viewpoint. A Turing machine is an abstract device with an unbounded tape and unending patience, a model that does not pretend to be a blueprint for hardware, but that captures the logic of procedures carried out step by step. The assumption of unbounded memory and time lets us ask what can be computed in principle if resources can be extended without limit. Results like the unsolvability of the halting problem use diagonal patterns related to Cantor's to show that there are questions no algorithm can settle. Infinity here marks the boundary of mechanical knowability, not because the world contains an actual infinite machine, but because the model tells us what would happen if we never had to stop. Topology and geometry also make strategic use of ideal points at infinity without claiming that space literally contains them. By adding a single point at infinity to the complex plane, one obtains a sphere on which every rational function behaves in a uniform way. In projective geometry, parallel lines meet at a point at infinity, and that convention streamlines the theorem so that special cases do not have to be carved out. These devices are not mystical. They are bookkeeping tools. They show again how the infinite can be introduced in a controlled way to make structure explicit. At the human scale, there is something quietly consoling about this. We do not need to outrun finitude to reason clearly about what lies beyond every fence. The patient use of limits lets us talk honestly about destinations we never reach, just as the patient use of cardinalities lets us compare sizes we never finish counting. The more one works with such ideas, the less mystical they feel and the more workmanlike. Infinity becomes not a thunderclap, but a steady light that allows fine distinctions to be seen. And yet the subject cannot help stirring a gentler feeling at the edges of reason. To recognize that there is no final largest number to name, no final smallest interval to inspect, no final member of the list of questions one might ask, is to experience a kind of humility that is not the same as defeat. It is the humility of standing on a shore and seeing that the horizon will move as you walk toward it. You are not expected to arrive. You are invited to keep going. If you step outside at night and look up, your eyes meet no wall. The stars are not evidence by themselves that space is truly infinite, and the question of the universe's size will be reserved for later. What the moment does reveal, even before the astronomy, is how natural the unbounded feels to the mind. You draw lines between points and extend them without instruction. You imagine patterns continuing. You accept that there could always be one more star just beyond the last you can see. That everyday gesture is as close to the heart of the concept as any technical definition. So the answer to what we mean by infinity at the beginning of a long exploration is both modest and exact. We mean the absence of a final bound, expressed in ways that are precise enough to be trusted. We mean the capacity to talk about processes that never finish and sizes that cannot be listed, in a language that makes their behavior calculable. We mean a method that turns "keep refining" into "here is the value," a structure that distinguishes the countable from the uncountable, and a completion that welcomes the limits our own processes generate. That meaning will be enough to carry us into paradoxes, into geometry, and into questions about space and time, each in its own chapter. Chapter 2. The Paradoxes of Endless Processes. Paradoxes where infinity stops being an innocent word and starts doing real work. When a process refuses to end, when a justification calls for another justification, when motion is analyzed into infinitely many stages, common sense reaches for familiar rules and discovers those rules do not apply. The shock is productive. Historically, it is precisely at the points where our everyday expectations fail that mathematics, logic, and science have been forced to sharpen their methods. Paradoxes built from endless processes are not ornaments around the edge of understanding. They are the grindstones that shape it. One of the oldest and most persistent of these grindstones is the infinite regress of causes. If every event requires a cause, and every cause is itself an event, then the chain seems to extend backward without limit. A world with no initial link looks, to some temperaments, incomplete, as if explanation were always being deferred. A world with an initial link looks, to other temperaments, arbitrary, as if explanation had simply been stopped by fiat. Philosophers have moved between options. Some argue for a first cause that is not itself caused, an unmoved mover that halts the regress without violating the demand for explanation. Others accept the regress as benign, on the grounds that a chain can be intelligible even if it has no first link. the way an infinite series can be meaningful even though it lacks a last term. Still others treat causal talk as local and pragmatic, meant to organize patterns within a segment of the world rather than to reach an ultimate ground. The regress does not settle the question, but it forces those who care about causes to say exactly what they mean by explanation, what they take a cause to be, and what standards they will accept for stopping or continuing an account. A parallel kind of regress haunts epistemology, the study of knowledge and justification. If every belief needs a reason, and every reason needs a further reason, we seem driven backward forever. Foundationalists reply by positing beliefs that do not require further support, such as basic perceptual judgments or logical axioms. Coherentists reply by changing the shape of justification. Rather than a chain anchored at one end, justification becomes a network where beliefs support each other in a mutually reinforcing web. A third position, infinitism, bites the bullet and allows an endless chain of reasons, arguing that it is the availability of further reasons in principle, not their completion, that does the normative work. The paradox of regress, here as in causation, functions as a pressure test. It makes a vague picture precise by demanding a structure, a base, a web, or an open-ended path with clear rules for how each step earns its place. When infinite processes are packed into a finite interval, the tension becomes especially vivid. A modern emblem is the so-called Thomson's lamp. Imagine a lamp that is switched on after half a minute, off after a quarter minute more, on after an eighth, off after a 16th, and so on, the intervals halving each time. After 1 minute, infinitely many switchings have occurred. Is the lamp on or off at the 1 minute mark? No finite stage decides the question, because for each stage there is another that occurs later, but still before the minute passes. The puzzle teaches a lesson about limits that mere slogans cannot supply. A limit is not a property that must be inherited from any finite stage. It is a property defined by how the values behave as the stages progress. In standard mathematics, the sequence of on and off in Thomson's construction does not converge to a single settled state, so the setup is best treated as an instruction without a determinate result. What the lamp paradox really shows is that completing infinitely many actions in finite time is a phrase demanding careful interpretation. In physical theories that respect signal speeds, energy constraints, and non-zero switching times, the setup cannot be realized at all, and so the apparent contradiction is a map of where physics draws a line between the imaginable and the possible. A cousin to the lamp is the Ross-Littlewood urn process, where balls are placed into and removed from an urn in an infinite schedule that nevertheless leaves the urn empty at the limit. For example, at the first step, you put in balls numbered 1 through 10 and remove ball 1. At the next step, you put in balls 11 through 20 and remove ball 2, and so on, having the time between steps each round. Every step leaves 9 more balls than before, and yet, after completing the infinite schedule, no particular ball remains, because each has been removed at a finite stage. The paradox converts puzzlement into precision. It forces a distinction between the number present at each finite stage and the status of any specific item when the sequence of stages is exhausted. The lesson pushes us toward pointwise versus uniform reasoning, toward quantifiers in the right order, toward the recognition that for every ball there exists a stage, behaves differently than there exists a stage for every ball. Endless procedures illuminate probability as sharply as they do logic. In a continuous probability distribution, the chance of selecting any exact real number is 0. yet some exact number is always selected. For a beginner, that sounds like double talk. The paradox survives because probability zero is a measure-theoretic statement about size, not a claim of impossibility. The set of outcomes with probability zero can be non-empty. It is only sets of measure zero, not events ruled out by the model, that receive the value zero. Without the discomfort of paradox, the distinction between impossibility and zero measure would not have been pressed into clarity, and modern probability would be a loose collection of intuitions instead of a precise calculus that tolerates infinity gracefully. Decision theory and economics accumulate their own paradoxes once infinity enters. The St. Petersburg lottery is the most famous. You flip a fair coin until it lands heads. If the first heads arrives on the first toss, you win a modest sum. If it arrives on the second toss, you win twice as much, on the third twice again, and so on. The expected monetary value of the game diverges. In the pure model, a rational agent with strictly expected value preferences should be willing to pay any finite amount for the privilege of playing. In practice, nobody does. The paradox forced a re-examination of how expectations should be modeled, leading to utility functions that encode diminishing marginal value and to risk-sensitive preferences. Infinity did not turn practical reason to nonsense. It made visible the hidden assumptions under which the initial calculation proceeded, and thereby made the theory better. Not all paradoxes featuring endless steps involve time. Some live in space, and they wield infinity to fracture geometrical intuition. The Banach-Tarski result proves that, given the axiom of choice and the infinite richness of three-dimensional space, one can decompose a solid ball into finitely many disjoint pieces and reassemble them into two balls each congruent to the original. The pieces are not measurable in the usual sense and cannot be realized as physical chunks. The paradox belongs to a realm where sets are allowed to be as wild as logic permits. The effect on foundations was salutary. It made clear which results depend on choice, which arguments require measurable sets, and where our geometrical intuitions are reliable guides. Paradox again pushed mathematics to state its assumptions and accept their consequences. The most delicate family of paradoxes are those in which an endless sequence of demands blocks a perfectly possible outcome. Bernardetti described a traveler on a path who will be stopped by an infinite sequence of barriers, each of which would be erected only if he reaches a certain point that is strictly nearer than the previous barrier. No barrier is ever erected because the traveler never reaches the trigger point for any single one. And yet the infinite array of conditional threats prevents him from moving at all. Grim Reaper variants replace barriers with potential killers, each poised to act earlier than the next. The constructions are not blueprints for the world, but pressure tests for our causal intuitions. They reveal how fragile certain informal principles are when stretched across infinitely many conditions, and they provoke technical refinements in theories of time, causation, and counterfactuals that prevent contradictory sets of triggers from being assembled. Paradoxes tied to infinite sums are another arena where common sense fails and method must intervene. Series that do not converge in the ordinary sense can sometimes be assigned values by more forgiving summation methods, and those assignments can be both consistent and useful when handled with care. The infamous declaration that the sum of all natural numbers equals a negative fraction is, strictly read, a statement about a regularization scheme, not about ordinary addition. Misread, it is nonsense, properly understood. It is a tool that appears inside analytic continuations used in physics. The important thing is not that an attention-getting equation can be written, but that endless addition obeys different rules depending on which limits exist and which sense of convergence is in play. Paradox advertises the need for those senses to be distinguished and their domains of legitimacy to be marked. Even in basic geometry and analysis, infinite processes strain the link between the part and the whole. Rearranging the terms of a conditionally convergent series can alter its sum, violating the expectation that order should not matter. The Riemann rearrangement theorem shows precisely under what conditions the order of an endless addition is harmless and under what conditions it is decisive. If our experience were confined to finite sums, we might never have suspected that order could matter. The paradox announces the difference, and the theorem classifies it. The same moral holds for integration and differentiation under the integral sign, for exchanging the order of limits for interleaving infinite quantifiers. Where finite practice suggests a freedom, paradoxes show us the price of exercising it without a license. The logical shape of these lessons can be seen in the very bones of mathematics. Induction is a method tailored to the natural numbers precisely because they are well ordered in a way that blocks infinite descent. If regress were tolerated freely, proofs by induction would fail, recursion would not terminate, and definitions built stage by stage would be ungrounded. Axiomatic set theory includes a foundation axiom that prevents membership chains from looping or descending infinitely, not because such chains are literally observed in nature, but because disallowing them keeps the notion of building a set from earlier sets coherent. Where paradox presses logic the hardest, the result is not a surrender, but an explicit structural constraint that makes the rest of the theory safe to use. Science has felt the same pressure and has responded in the same way. Cosmology frames debates about the beginning of time in language that acknowledges the hazards of both options. A beginning raises questions about what it means for time to start, whether there can be causes before the first moment, and how to interpret boundary conditions when there is no earlier state. An eternal past raises worries about traversing an actual infinity to reach the present, and about the stability of models that extend backward without bound. These are not puzzles to be solved by slogan. They are invitations to make models precise enough to say what time means in each, how geodesics behave, which singularities are physical and which are artifacts of idealization, and how evidence should be weighed when observational access to the deep past is indirect. Infinity sharpens cosmology not by answering the regress, but by rewriting the questions in operational terms. Physics likewise treats divergences, places where quantities blow up under calculation, as warnings. Early quantum field theories produced infinite answers for measurable quantities, an outcome as paradoxical as it was useless. The renormalization program turned a field of infinities into a predictive framework by showing how parameters measured at one scale swallow the infinities that arise from the contributions of shorter scales. The paradox of infinite answer did not vanish. It was reinterpreted as a sign that naive counting across scales misses the way nature organizes itself. The result is a general method that respects the fact that physical laws can change with scale, and that infinity is a limit to be managed, not a number to be feared. Computer science translates paradoxes of endless process into limits on what can be decided. An algorithm that searches indefinitely for a counterexample and halts only if one is found is a perfectly coherent procedure, but without a bound on search time, No finite observation can certify that the algorithm will never halt. The halting problem takes this phenomenon to its logical endpoint, proving that there can be no universal decision procedure for predicting the stopping behavior of arbitrary programs. Accelerated computers that complete infinitely many steps in finite time, so-called xenomachines, dangle the lure of evading this limit, but their incompatibility with physical constraints repeats the lesson from the lamp. Mathematics can conceive an endless schedule. Physics blocks its realization in the world we inhabit. The boundary is instructive. It tells us which impossibilities are logical and which are physical, and it keeps our ambitions for automation honest. There is a social and cognitive dimension to all this. Paradoxes are not only technical problems, they are training exercises in intellectual hygiene. By confronting a scenario that defeats common sense, one learns to separate feel from proof, image from definition. The first time a student sees a bijection between the whole numbers and the even numbers, the instinct that a part must be smaller than the whole cries out. The first time a student watches a sequence converge without ever showing its limit at a finite stage, the instinct that, to get there you must arrive somewhere, protests. These protests are not mistakes to be shamed. They are the raw material from which refined concepts are made. Paradoxes force the work of refinement to happen in the open. If paradoxes based on endless processes have a unifying moral, it is that infinity breaks common sense precisely so that method can be rebuilt. A regress of causes teaches us to declare what counts as an explanation and when explanation must stop. A regress of reasons teaches us to fix the shape of justification and to own the commitments that shape demands. Supertasks teach us to define limits carefully and to distinguish mathematical possibility from physical feasibility. Measure zero events teach us to keep impossibility and smallness apart. Divergent sums teach us to mark the boundaries of rearrangement and to keep track of the order in which we do and then keep doing. Each surprise unlocks a refinement, and the body of refinements is what we call mature theory. Stepping back, there's a quieter reflection to allow. If some questions always open onto further questions, if some explanations always invite an earlier explanation, if some analyses always expose another layer of detail, we should not be surprised. Endless process is not the enemy of understanding. It is one of its shapes. The paradoxes that announce its presence can feel destabilizing on first encounter, but they are also the tools with which clarity is won. A mind that learns to live with an open chain learns also to ask better questions at each link. Perhaps there is no final point at which all inquiry rests, and perhaps that is not a failure, but a feature of a world where depth does not run out. Your life is finite, your reasoning finite, but the path of and then is always there, and walking it, carefully, methodically, turns paradox into understanding without promising the last word. Chapter 3. Infinity in Mathematics, the Countable and the Uncountable. There is a moment in the history of ideas when infinity stopped being a diffuse haze at the edge of thought and became an object with crisp internal structure. That moment belongs to Georg Cantor. Before Cantor, mathematicians used infinity mostly as a manner of speaking about processes that could be carried on without end. A sequence that keeps refining, a sum with more and more terms, a curve examined at ever finer scales. After Cantor, the infinite could be compared, measured, and stratified. The move was not rhetorical. It rested on precise definitions and proofs. It said, in effect, that some infinities are strictly larger than others, and that there is a principled way to tell which is which. Cantor's program did not abolish the older process-based view. Instead, it added a complementary perspective, the view of infinite collections as completed totalities whose sizes can themselves be studied. The instrument that makes this comparison possible is simple to state and far-reaching in consequence. Two collections have the same size when their elements can be paired one-to-one so that nothing in either set is left unmatched. For finite sets, this criterion merely repackages counting. If there is a perfect pairing, the sets have the same number of elements. For infinite sets, the criterion is revelatory. Consider the whole numbers and the even numbers. Intuition says the evens should be half as many, and yet there's a perfect pairing that sends each whole number n to the even number 2n. No even number is missed, and no two whole numbers are paired with the same even. The pairing shows that the two sets have the same size in Cantor's sense. What looks paradoxical by the standards of everyday counting is routine once one accepts one-to-one correspondence as the measure of size. From this vantage point, the first tier of infinity can be described cleanly. A set is countable if its members can be arranged in a single infinite list so that each appears at some finite position. The whole numbers are countable by definition. The integers are countable because a list can alternate positive and negative values while increasing their magnitude. The rational numbers, at first glance too numerous to hope to list, are also countable. They can be placed on a two-dimensional grid whose rows and columns are indexed by integers. A diagonal traversal of the grid reaches every fraction in lowest terms. The success of that traversal jars intuition because it collides with another true statement. The rationals are dense on the real line, meaning that between any two distinct real numbers, there is a rational. Density is a local property about what one sees in every small interval. Countability is a global property about whether a single list eventually reaches every member. Both claims are correct. The tension between them is lesson, not contradiction. That lesson prepares the mind for Cantor's central discovery. The continuum of real numbers is not countable. The real numbers include every possible decimal or binary expansion. Rationals appear as terminating or repeating expansions. Irrationals appear as expansions that never settle into a repeating loop. Some irrationals are defined by algebraic equations, others arise as limits of series or by geometric constructions, and most have no succinct description. Cantor proved that no sequence can capture all reals. The proof is the diagonal argument. Assume, for contradiction, that the real numbers between 0 and 1 have been listed in a sequence. To avoid technicalities about alternative decimal representations, imagine the list written in a base that lets us avoid the all nines overlap, or stipulate that when a number has two expansions, we choose the one without trailing repeating maximal digits. Now scan down the list along the diagonal, taking the first digit of the first number, the second digit of the second number, the third of the third, and so on. Alter each of these diagonal digits, change each to some other digit, and assemble the altered digits into a new expansion. By construction, the new number differs from the first listed number in the first digit, from the second in the second digit, and so on. Therefore, it is not equal to any entry in the list. But it is still a real number between 0 and 1. The assumption that there was a complete list was false. No enumeration can succeed. The conclusion is exact. The set of whole numbers and the set of real numbers do not have the same size. The first is infinite and listable. It is the smallest infinite size. The second is infinite but unlistable. It is strictly larger. The diagonal method is persuasive because it produces a specific counterexample from the data of any proposed list. The argument neither relies on imagery of continuous lines nor appeals to vague feelings about vastness. It hinges on a clear construction and the simple fact of disagreement at each indexed position. The method also scales. It does not merely show that one particular enumeration fails, it shows that every possible enumeration must fail for the same structural reason. Cantor went further. He proved a general theorem. For any set whatsoever, the collection of all its subsets is strictly larger than the set itself. The proof again has a diagonal flavor. If one tries to pair elements of a set with its subsets, one can define a contrarian subset that, for each element, includes that element precisely when the subset paired to it leaves it out. That contrarian set cannot be the subset paired with any element, for it disagrees with each at the corresponding point. Therefore, no pairing can be complete. The consequence is sweeping. There is no largest infinity. Given any infinite set, one can move to a strictly larger size by passing to the family of all its subsets. Iterating that passage generates an unending hierarchy. To navigate that hierarchy, Cantor introduced notations and methods for talking about infinite sizes on their own terms. On one side sit ordinal numbers, which index positions in well-ordered sequences and allow transfinite induction, a method of proof that climbs through ordered types extending beyond the finite. On the other side sit cardinal numbers, which measure pure size. The smallest infinite cardinal is the size of the whole numbers. The size of the real numbers is larger. Between and beyond them lie many other sizes whose arrangement cannot be fully settled by the most common axioms of set theory. The existence of this hierarchy was the surprise. The ability to reason within it became a new part of mathematical craft. Placed in its historical setting, the story is startling. The 19th century had already rebuilt analysis with sharpened definitions of limit and continuity, and had constructed the real numbers from the rationals in ways that guaranteed completeness. Many mathematicians still preferred to treat infinity as potential rather than actual, as a manner of speaking about procedures that could be prolonged but never finished. Cantor's insistence on completed infinite sets and on proofs that compare their sizes directly met resistance. Leopold Kronecker famously objected to existence proofs that did not supply explicit constructions. Others worried that the move would license paradoxes or loosen the bond between mathematics and computation. Yet Cantor's theorems could not be dismissed without abandoning parts of analysis that had already proved their worth. Over time, the community learned to distinguish methods and domains. Constructive techniques, where they are demanded, non-constructive arguments where they illuminate structure, and careful attention to which background assumptions are in play. Paradoxes did appear, not in Cantor's theorems, but in naive set formation. If one allows any property whatsoever to determine a set, contradictions arise. Russell's paradox shows that the set of all sets that do not contain themselves cannot exist without contradiction. The Burali-Forti paradox shows that trying to collect all ordinal types into a single set fails. These discoveries did not topple Cantor's insight. They pressed mathematicians to articulate rules for set formation. Axiomatic set theory provided those rules. In the most widely used framework, sets are built in stages by operations that are powerful enough to support ordinary mathematics while restricted enough to block the paradoxes. The axiom of choice, a principle that asserts the ability to make selections from families of sets, emerged as a subtle ingredient, sometimes indispensable, sometimes the source of counterintuitive consequences, always a point to be flagged when invoked. At the heart of the subject sits a question that shaped 20th century logic. Is there a size of infinity strictly between the countable and the continuum? Cantor suspected that there is not. He framed this as the continuum hypothesis. David Hilbert placed it first on his famous list of problems in 1900, signaling that it captured something essential in the new landscape. The eventual resolution came in an unexpected form. Kurt Gödel showed that if the usual axioms of set theory are consistent, then adding the continuum hypothesis does not create contradiction. Paul Cohen later showed that if those axioms are consistent, then adding the negation of the continuum hypothesis also does not create contradiction. The hypothesis is independent of the standard axioms. It can neither be proved nor refuted from them. Independence results of this kind changed how mathematicians think about foundations. They do not say that truth is arbitrary. They say that some questions about the hierarchy of infinity cannot be answered without making additional explicit commitments. While foundational debates unfolded, the countable-uncountable divide quietly shaped everyday methods across mathematics. Measure theory was designed to assign sizes to sets in ways compatible with limits and to justify sophisticated forms of integration. In that setting, the rationals, despite their density, have measure zero. In the precise sense used there, they occupy no length along any interval. By contrast, sets built with the axiom of choice can be so irregular that they cannot be assigned any measure at all, while still respecting the rules of the theory. Between these extremes lies a rich hierarchy of definable sets: Borel sets built from open sets by countable operations, and Lebesgue measurable sets formed by countable refinements that carry robust regularity properties. The language of almost everywhere, null sets, and full measure depends on countable additivity, and countability is the hinge on which the proofs turn. Topology imports complementary lessons. Many spaces that analysis favors are separable. They contain a countable dense subset and admit a countable base of open sets. In such spaces, arguments can be carried out using sequences, and diagonal methods with sequences often suffice. When these countable features are absent, familiar theorems can fail or demand reformulation, and proofs must use more general devices than sequences. Functional analysis flourishes in settings where countable orthonormal bases exist, making expansions and approximations manageable. Descriptive set theory studies spaces, such as the classical Polish spaces, whose topological and measure-theoretic behavior is tightly controlled by countable structure. Across these subjects, the presence or absence of countable scaffolding dictates which tools are available. Computability theory throws the divide into sharp relief. There are only countably many algorithms because algorithms can be encoded as finite strings over a finite alphabet, and such strings can be listed. Consequently, only countably many real numbers can be computed to arbitrary precision by a program. Yet the reals are uncountable. It follows that most real numbers, in the sense of cardinality, are uncomputable. They cannot be produced by any systematic method, and they cannot be fully described by any finite script. Kolmogorov complexity makes this sharper. Only countably many finite descriptions exist, so only countably many reals are compressible in that sense. Almost every real number is algorithmically random, bearing no pattern that a finite program can exploit. The statement sounds philosophical when first heard, but it is a concrete consequence of the countable-uncountable divide. Inside analysis itself, The countable does much of the heavy lifting. Completeness of the real numbers is expressed in terms of Cauchy sequences, which are countable arrays of approximations that draw closer and closer. Convergence theorems for families of functions are typically formulated with countable quantifiers. Compactness arguments pass from infinite coverings to finite subcoverings by countable refinements. Rearrangement theorems warn that conditionally convergent series can be reordered to alter their sums, reminding us that endless addition behaves differently from finite addition, and that the order in which countably many steps are taken matters. These techniques are not accidents. They reflect the deep fact that countability provides just enough structure to control limiting processes without collapsing them back into finiteness. The same framework clarifies phenomena that might otherwise look paradoxical. There is a one-to-one pairing between the points of any interval of non-zero length and the points of the entire real line. In the sense of cardinality, a short segment is as numerous as the whole. A smooth, strictly increasing function can be written that maps the segment onto the line, ensuring that no points are missed. The sense of absurdity that sometimes accompanies this fact dissolves once one keeps track of which concept of size is in play. Cardinality asks only whether a pairing exists. Measure answers a different question: how much length a set occupies. Topology answers another: how the set sits with respect to open neighborhoods. The countable-uncountable distinction threads through these notions without replacing them. Educational and cultural effects were as significant as technical ones. Once students learned that infinity has different sizes, they also learned to demand precision about which notion of size is relevant in a given argument. They meet a repertoire of standard constructions that become part of their mental toolkit: enumerations of the integers and rationals, diagonal proofs of uncountability, examples that show how choice can produce pathological sets, and regularity theorems that protect analysis from pathology when definability and countability are present. The story of how these tools were forged, of resistance, revision, and eventual routine, belongs to the intellectual culture of mathematics as much as to its content. Shockwaves continue at higher levels. Large cardinal axioms, which postulate very large infinite sizes with strong regularity features, have consequences for the structure of sets of reals and for combinatorial principles that echo through analysis and topology. Descriptive set theory organizes definable subsets of the continuum into hierarchies according to the complexity of their definitions and ties regularity properties to those levels. In many cases, theorems that hold for Borel or analytic sets fail for arbitrary sets, and the proof of this contrast leans on the existence of uncountable collections that evade countable construction. The landscape of what can be proved about the continuum is shaped by choices about which infinities one is willing to assume. The diagonal motif that divided the countable from the uncountable also radiated into logic and theoretical computer science. Arguments that no consistent, sufficiently expressive formal system can capture all arithmetic truths, and proofs that there is no general algorithm to decide whether an arbitrary program halts. Both share the same pattern: assume a comprehensive list, then construct an object that escapes by inverting a diagonal feature. These results are not about set theoretic size directly, but they express the same insight. Some domains are too rich to be captured by any single enumeration, and the method that reveals this richness is a cousin of Cantor's. All of these threads return to a central moral. The countable-uncountable divide is not an oddity to be admired and put away. It governs tactics and proofs. determines which tools are available, and explains why certain questions are formidable. It reveals that approximation by sequences is a privilege of spaces with countable scaffolding, and that in spaces without such scaffolding, one must move to more general devices. It explains why some collections can in principle be searched exhaustively, because a list exists to be traversed, and why others cannot be approached that way at all. It is the hidden architecture that supports measure theory, topology, functional analysis, computability, and large parts of logic. What began as a claim about sizes became a method for organizing thought. To call a set countable is to commit to an ordering that an argument can walk through step by step. To call a set uncountable is to accept that no such ordering can reach every member, and that one must reason by other means, by measure and category, by compactness and completeness, by indirect argument and diagonal construction, and by the carefully controlled use of transfinite methods. These habits have become part of the ordinary discipline of modern mathematics. They are not artifacts of fashion. They are responses to the way the infinite actually behaves. We live among countable things, days, names, steps, the finite projects that fill a life. Yet our reasoning rests on an uncountable background that no list could ever exhaust. Learning to be at ease with both truths is part of learning to think clearly, and perhaps part of learning to be at ease in a world where the inexhaustible is always nearby. Chapter 4. The Infinity of Geometry and Fractals. Geometry is where infinity becomes concrete. A single line segment, bounded and perfectly ordinary to the eye, already contains an unending depth. Between any two distinct points on that segment, there lies another point, and between any pair you choose from those, another still, in a descent without terminus. This is not poetry, but the working assumption of classical geometry, the continuum. When we model a line with the real numbers, every coordinate can be refined forever. There is no smallest tick on the ruler, no final grain of space inside the model. That idealization lets mathematics speak with exquisite accuracy about motion, shape, and size, because any error can in principle be pressed smaller. It also invites puzzles. If a line is made of points and each point has no length, how does a collection of lengthless things add up to something with length? The answer belongs to measure theory rather than to everyday intuition. Length is assigned to sets that have the right regularity, and the uncountable structure of the continuum allows a positive total even though each point by itself carries none. The point is not that reality must be indefinitely divisible, but that the mathematical picture we use for length, angle, and curve has infinity coded into its smallest scales. The infinite divisibility of the line is most vivid when contrasted with digital experience. On a screen, a segment is a staircase of pixels. Zoom far enough and edges turn blocky. In the model, no such coarseness appears. Zooming simply reveals more points that were always there. This idealization underwrites calculus, where the slope of a curve at a point is defined by letting the interval used to compute rise over run shrink without bound. It underwrites analytic geometry, where equations draw curves whose coordinates can be specified with as many digits as one wishes. The continuity of the line is not an empirical claim about atoms of space. It is a decision to use a model in which there is never a smallest interval. Because that decision pays off in prediction and design, it remains the language of geometry, even as physics explores questions about whether nature itself respects a smallest scale. The idea that between any two points lies another does not merely guarantee density, it multiplies structure. Consider how one might try to list all points of a segment the way one lists the whole numbers. No such list can succeed because the real line is not countable. If someone hands you an ordering, you can always find a point missed by stepping diagonally through the purported list of expansions and changing digits. The consequence for geometry is subtle but profound. A finite piece of line is, in the sense of pure size, beyond enumeration. That inexhaustibility shows up in analysis when we ask whether every continuous curve has a derivative at every point. It does not. Or whether every curve that looks smooth at a distance is composed of well-behaved pieces. Many are not. The continuum is hospitable to wildness. One emblem of that wildness is the existence of continuous curves that are nowhere differentiable, whose tangent direction never settles even at the smallest scales. The classical Weierstrass function provides such an example. At any magnification, its graph is crinkled, with no interval on which the turmoil rests. Even as its oscillations remain bounded, its fine structure refuses to simplify. The straight edge you bring to the page cannot find a single point at which the graph agrees with a line to first order. The discovery that such functions exist, and indeed that they are abundant, altered the 19th century picture of curves. Infinity at small scales is not only a matter of squeezing more points into intervals, it is a matter of allowing shapes whose detail persists under every attempt at smoothing. That persistence is the doorway to fractals. A fractal is a set or curve whose structure repeats across scales, sometimes exactly, sometimes statistically. Look closely and you see shapes within shapes, each echoing the whole. The defining feature is self-similarity coupled to a notion of dimension that can take non-integer values. Ordinary curves have dimension 1, ordinary regions have dimension 2, and solids have dimension 3. Fractals sit in between, occupying space more densely than a line, but less than a full region. This in-between dimension, formalized through Hausdorff and related notions, quantifies roughness. A curve with fractal dimension greater than 1 has length that grows as you measure it with finer rulers. And for some classical constructions, the growth is unbounded. The length becomes infinite, even though the curve is contained in a bounded region. The geometry of fractals, then, is not merely decorative. It is a calculus of roughness that captures how detail scales. The Koch snowflake is a paradigm. Begin with an equilateral triangle. On each side, replace the middle third by the two sides of a smaller outward-pointing triangle, creating a starry notch. Repeat this replacement on every new segment forever. The resulting curve is continuous, closed, and jagged at every scale. Its area approaches a finite limit, the region enclosed converges, but its perimeter grows without bound. At each stage, you add a fixed proportion of length to what was there before, and because there are infinitely many stages, the total outruns any finite bound. The resulting boundary has a precise fractal dimension strictly between 1 and 2, mirroring its dual nature as more than a line yet less than a filled region. The snowflake is not a portrait of any physical crystal. Real snowflakes grow by diffusion and temperature-controlled branching, but the construction dramatizes how infinity can be stored in small-scale geometry. No matter how far you zoom, new edges appear. Other classical constructions make the same point from different angles. The Sierpinski triangle begins with a filled triangle and then removes the central triangle of each stage, leaving the lace of ever smaller holes. The Cantor set begins with a line segment and removes middle thirds again and again forever, producing a dust of points spread across the interval with no intervals left. Each is self-similar. Each has zero area or length in the usual sense while containing uncountably many points, and each forces a reconsideration of what it means for a set to be large. Large for cardinality need not be large for measure. Large for measure need not be large for topological presence. The interplay of these notions, exposed by infinite iterative procedures, is the daily work of modern geometric analysis. Fractals are not confined to the blackboard. Nature routinely displays patterns with approximate self-similarity across scales. Coastlines offer the classical example. When Louis Fry Richardson sought to measure national boundaries, he noticed that reported lengths depended on the size of the measuring stick. Smaller sticks hugged the inlets and promontories more closely, increasing the total. There seemed to be no single true length independent of scale. Benoit Mandelbrot reframed this coastline paradox as a signature of fractal geometry. Real coastlines do not repeat indefinitely. Wave energy, rock type, and sediment processes impose a finest meaningful scale. Yet across substantial ranges, they exhibit statistical self-similarity, and a fractal dimension can be assigned to quantify their roughness. Two shores can look equally jagged to the eye, while possessing different dimensions because their detail accumulates differently with magnification. Clouds and mountain profiles share the theme. Cumulus fields fragment into puffs whose edges evince new scallops under magnification, a sign of turbulent mixing and condensation, evaporation fronts that create similar structures across scales. Mountain ranges erode into ridges and subridges. Satellite views reveal drainage basins and subbasins that branch in patterns reminiscent of recursive construction. The point is not that nature draws perfect copies at each level. It is that the mechanisms at work, erosion, deposition, flow instabilities, apply repeatedly in ways that blur the distinction between small and large. When processes are scale-free over a range, geometry inherits a scale-free look. Lightning offers another illustration. An ionized channel seeks the path of least resistance through air whose microscopic inhomogeneities are everywhere. Branches form and then sub-branches. Screening and field enhancement steer new leaders into spaces between old ones, and the whole appears as a dendritic structure with repeating motifs. Snowflakes grow by the interplay of diffusion and attachment at their tips. Sixfold symmetry emerges from the crystal lattice, but the branching that fills arms with fern-like detail reflects diffusion-limited growth. In both cases, idealized models, diffusion-limited aggregation, Laplacian growth, reproduce the qualitative structure by iterating simple rules that embed infinity at small scales. Add new growth at the places where a field is strongest, then recompute the field and repeat. The final forms are not prescribed in detail from the start. They are the record of a process allowed to run. Because natural fractals are only approximately self-similar over finite ranges, measuring their dimension is necessarily tied to method. Box counting procedures estimate how the number of small boxes needed to cover a set grows as the box size shrinks. Slopes on log-log plots translate into dimension estimates. If the slope is stable across scales, self-similarity is present. If it bends, different mechanisms dominate at different scales. These empirical techniques do not replace formal definitions. They are the practical side of bringing fractal language to data. The reward is a vocabulary for roughness that is more quantitative than adjectives and more informative than single number length or area. Fractal thinking also clarifies why simple curves can be longer than they look. Imagine tracing a coastline on a map with a divider set at a fixed span and counting steps. Halve the span and you find more steps, not merely because you take more of them, but because previously unseen indentations become visible. In the limit of vanishing span, a mathematically ideal fractal boundary explodes in length. Real boundaries plateau because rock grains, tidal cuts, and biological microstructures set a floor under which the concept of coastline loses meaning. The plateau is not a failure of fractal geometry. It is a reminder that mathematical infinity is a model of behavior, not a claim about the world's indivisibility. The same distinction guides the understanding of curves in analysis. Some curves are rectifiable, their length is finite, and can be approached by polygonal approximations whose total length converges. Others are not. A nowhere differentiable curve may still be rectifiable, but many canonical fractals are not, because the added detail at each stage contributes a fixed proportion to the total length, and the accumulation never abates. Wherever infinite iteration appears, questions about rectifiability, area, and boundary regularity follow. Geometric measure theory was built to answer them, blending topology, calculus, and measure to study sets whose boundaries are too rough for classical methods. Concepts such as perimeter in the sense of Cacciopoli or finite perimeter sets allow analysis to extend into domains that look fractal at the eye's resolution. Self-similarity has an exact version in the realm of complex dynamics. The Mandelbrot set, a compact region in the complex plane defined by a simple quadratic iteration, contains an infinity of detail. Zooming into its boundary reveals bulb and filament patterns that repeat with variation. Tiny replicas of the whole appear at different locations, adorned with spirals and dendrites that encode the dynamics of nearby parameter values. The set is not generated by drawing a blueprint of filigree in advance. It is the loci of parameters for which the corresponding iteration remains bounded, and the fine structure records how stability is lost. The mathematics behind the pictures is deep, connecting iteration, conformal mapping, and the combinatorics of external rays, but the visual moral suffices for our theme. Infinite complexity can be born from iterative rules of extreme simplicity. In engineering and technology, the same scaling ideas become tools. Antennas patterned with fractal motifs pack long effective path lengths into small areas, helping them operate efficiently across multiple frequency bands. Compression schemes analyze images for self-similar blocks, reconstructing detail by repeating a mapped pattern instead of storing each pixel. Terrain in computer graphics is synthesized by superposing noise at many scales, a statistical self-similarity that mimics the roughness of real landscapes. Blood vessels and bronchial trees branch to distribute flow efficiently. While biology does not implement exact mathematical fractals, the pressure to deliver resources across volumes with minimal material induces branching patterns that occupy space with an economy similar to that captured by fractal dimension. In each case, the geometry of repeated structure across scales is harnessed for performance. What, then, is the status of infinity in geometry as we encounter it in the wild? In pure mathematics, the continuum remains the basic canvas, and fractal constructions are truly infinite in their descent. In nature, mechanisms have cutoffs. Molecules, grains, and thermal noise end the cascade. The success of the model does not depend on whether infinity is physically realized. It depends on whether the processes in question maintain scale-free behavior across enough octaves for fractal laws to dominate observables. When they do, the language of dimension and self-similarity explains measurements better than smooth approximations do. When they do not, classical geometry resumes command, and the jaggedness washes out at coarse scales. This coexistence is not a compromise, but a strategy. The same river network can be seen as a graph of stream orders at one scale, as a fractal basin boundary at another, and as a smooth curve across the page at a third. A cloud bank can be modeled as turbulent fractal interface for radiative transfer and as a smooth field for large-scale circulation. The unifying lesson is that geometry is not a single portrait, but a family of portraits indexed by scale, and infinity is the hint that there is always another picture if you step closer. Even within mathematics, the invitation to infinite detail is tempered by structure. Not every rough boundary is uncontrolled. Quasi-conformal maps tame some fractal edges by bounding how much they can distort shapes. Regularity results tell you when solutions to partial differential equations produce interfaces with a known degree of smoothness, and when instabilities drive those interfaces toward roughness. The geometry of minimal surfaces, crystal growth, and free boundaries sits at the crossroads, where energetics either suppress or amplify fine detail. Fractals are the outcomes when amplification wins, and smooth curves are the outcomes when smoothing forces prevail. Seen against the first half of our journey, this chapter's emphasis is complementary. Earlier we treated infinity in counting and in sets, where the unending shows itself in size. Here infinity lives in detail. It hides in the folds of a curve, in the branching of a tree, in the wobble of a graph that never resolves into a straight touch. The tools differ, but the logic is sibling to what we have learned already. Precise definitions rescue our reasoning when intuition is overwhelmed by abundance. Fractal geometry does not discard the line and the circle. It extends the vocabulary so that jaggedness can be spoken of with the same authority as smoothness. The world you move through is smooth from far away and rugged up close, and there is always a closer view. Your life is the same. The more you look, the more there is to see, and the seeing does not run out. Chapter 5. Infinity in Physics, Space Without End. When physicists talk about an infinite universe, they do not mean a place that stretches into some external void, linearly and forever, with an edge waiting for you beyond the last star. The modern picture is more precise and, in its precision, stranger. It begins with the idea that space itself is a geometric object whose properties are determined by matter, energy, and the dynamical law encoded in general relativity. In that framework, the universe can be spatially finite or spatially infinite, and either option can lack a boundary in the everyday sense. The distinction that matters is not whether you would hit a wall if you traveled far enough, but whether the geometry closes on itself or keeps going, and whether your journey could, even in principle, return you to your starting point without ever turning around. The phrase finite but unbounded points to that possibility. Imagine living on the two-dimensional surface of a sphere. Your world has no edges. Walk straight ahead and you never meet a border. You simply circle the planet and eventually come back to where you began. The surface's area is finite, yet it is unbounded in the sense that there is no rim to step over. In 3 dimensions, there are analogous spaces in which every straightest possible path, called a geodesic, eventually loops, and yet there is no boundary anywhere. The classic example is a 3-sphere, the higher dimensional analog of the ordinary sphere. There are also more exotic possibilities, spaces that are locally flat with 0 curvature at each point, but whose global shape is that of a 3-dimensional torus, formed by identifying opposite faces of a cube. Those spaces, too, can be finite and unbounded. By contrast, a spatially infinite universe has no such closure. Its geodesics do not wrap. They stretch without limit. No amount of travel brings you back to where you began, because there is no global periodicity to the geometry. Cosmology describes the large-scale universe with models in which spatial slices evolve in time as the universe expands, all governed by Einstein's equations. The curvature of those slices can be positive, negative, or approximately zero, corresponding roughly to spherical, hyperbolic, or Euclidean geometry. Curvature is a local property. Topology is the global way those local neighborhoods stitch together. A nearly flat universe can still have a multiply-connected topology that closes on itself, just as a flat two-dimensional screen can be wrapped into a cylinder or a torus by gluing edges. Observations of the cosmic microwave background and of the distribution of galaxies suggest that, over the largest scales we can probe, space is very close to flat and uniform. That statement does not compel a verdict on whether space is globally infinite or merely very large and closed. It narrows the options and sets bounds. If space is finite and unbounded, its fundamental domain must be large enough that repetitions, multiple images of the same galaxies or characteristic matched circles patterns in the microwave background, do not show up within our observational reach. If space is infinite, the flatness suggests that its curvature radius is effectively unbounded on the scales we can test, which is a statement about geometry, not a proof of endless extent. The observable universe is not the same thing as the whole. We see only as far as light has had time to travel since the hot, dense beginning of the expansion. That distance defines a horizon, a sphere around us beyond which no information has yet arrived, not because there is nothing there, but because signals from there have not had time to reach us. The radius of this sphere, measured in the natural comoving coordinates that expand with the universe, is vastly larger than the simple light travel time would suggest. Expansion stretches distances while light is en route, so the farthest sources we can now receive signals from are presently much farther away than their light time in years. The horizon thus encloses a finite volume of space-time that is our past light cone. And when people give a size for the observable universe, they mean that volume's boundary at the present cosmic time. Everything beyond that boundary belongs to the total universe, but not to the observable part. As time passes, the observable sphere grows, admitting new regions to view. Because the expansion is currently accelerating, there is also a different horizon, the event horizon, that marks a limit to what we can ever influence or receive signals from in the far future. The two horizons are not the same, and together they remind us that the words near and far require careful definitions when space itself is dynamical. Whether the total universe is infinite is an empirical question constrained by theory and measurement. Inflationary cosmology, a framework in which the early universe underwent a brief, enormous accelerated expansion, tends to flatten space and to make the total volume vastly larger than the part we can see. In many versions of inflation, the process does not end everywhere at once. It continues in some regions while it stops in others, producing an ensemble of expanding patches. The result can be a universe that is at least effectively infinite in spatial extent, with our observable domain one garden in a boundless, ever-growing landscape. That picture is compelling for several reasons. It explains why the cosmic microwave background is so uniform across the sky. It generates the small, nearly scale-invariant ripples in density that grew into galaxies, and it offers a mechanism for driving space toward flatness on large scales. It is also a picture that requires restraint. The parts we can test are the predictions about statistical properties within our horizon. The claims about what lies far beyond are indirect inferences. They may be right. They are not the same as direct observation. If space is infinite, one implication is immediate and counterintuitive. Infinity does not merely mean more of the same. It means that if matter is distributed with a non-zero average density, and if the laws of physics are locally the same everywhere, then every configuration that is not forbidden by those laws appears somewhere, and in fact appears infinitely many times, separated by distances so huge that each appearance is causally isolated from the others. This is not mysticism, it is combinatorics. There are only finitely many ways to arrange matter at a given coarse-grained resolution inside a region the size of our observable universe. In a truly infinite space filled with enough such regions, those arrangements must repeat. The scale on which repetitions would occur is beyond astronomical. It dwarfs any number you could write down by stacking exponents, so the claim carries no practical consequences for observation. But as a statement about what infinity entails, it is crisp. Infinity turns rare into guaranteed somewhere. Even before invoking repetition, infinite space changes how total quantities are discussed. In a finite domain, one can sensibly talk about the total mass, or the total number of galaxies. In an infinite domain, those totals diverge. Cosmologists therefore use densities and correlations, mass per unit volume, number density of galaxies, statistical measures of clustering to describe the game is to specify fields and their fluctuations, not global sums. This shift is more than bookkeeping. In Newtonian gravity, an infinite, static, homogeneous universe is unstable and ill-defined because the net gravitational potential at a point depends on how one imagines summing contributions from infinitely many shells of matter. General relativity replaces that ambiguity with a consistent global description. A spatially infinite but uniform expanding universe is a legitimate solution, and local dynamics are computed with respect to that expanding background. Infinity is made mathematically meaningful by abandoning static intuition and adopting a dynamical framework where the field equations tell you how to scale your sums. The question of whether space has an edge often inspires the equally natural question: what lies beyond the edge, and into what does the universe expand? In the standard cosmological model, those are not meaningful questions. The expansion is not the swelling of galaxies into pre-existing emptiness. It is an increase of the scale factor that measures separations within space itself. There is no exterior into which the whole grows. The increase is intrinsic. A helpful mental picture is to think of locations in the universe as labels on a flowing medium. The labels drift apart according to a rule, and light traverses the medium at a finite speed. There is no outside room in which the drift occurs. There is only the rule and the labels. If space is finite but unbounded, infinity cedes its role and extent to a different kind of profundity. You can imagine a photon emitted in the early universe that, given enough time, wraps around and returns from the opposite direction. That return requires that the size of the fundamental domain be small enough compared with the time available and with the rate of expansion. In a rapidly expanding universe, even a finite fundamental domain can be too large for such circumnavigation to occur. Indeed, the lack of observed repeating patterns in the cosmic microwave background, such as pairs of circles with matching temperature variations that would betray a wraparound, places lower bounds on the size of a closed domain. To date, these bounds suggest that if space is closed, its closure scale is at least on the order of, and likely larger than, our observable horizon. The absence of evidence is not evidence of absence. It is a quantitative statement about how large the room must be, given the patterns we see. Against this geometrical backdrop, the content of the universe organizes itself into familiar structures. Galaxies form where slightly denser patches in the early plasma grow via gravity. They cluster into filaments and sheets that surround great voids, producing a web-like pattern when mapped across large volumes. In a spatially infinite universe, that web extends without end. There is no edge where the filaments stop. In a finite but unbounded universe whose fundamental domain is larger than our horizon, the web also appears effectively endless to any one observer. In either case, the practical astronomy of galaxies, clusters, and voids looks the same within the part we can see. Infinity enters not by changing the local rules of star formation or the virialization of clusters, but by changing the global context in which those rules play out. The most famous apparent clash between infinite space and observation is not about galaxies, but about darkness. If space is infinite and statically filled with stars, the night sky should be bright in every direction. Every line of sight would end on a stellar surface. The fact that the sky is dark was once framed as a paradox. The modern resolution is straightforward. The universe is not eternal and static with a uniform, unchanging distribution of luminous sources. It has a finite age since the hot, dense, early state. The oldest light we see is not starlight, but microwave radiation from when the plasma first became transparent, and the expansion redshifts light and dilutes energy density. The darkness of the night is a memorial to dynamics, not a contradiction with infinity of extent. If the universe is infinite, the abundance of potential arrangements raises conceptual problems for probability. In a finite sample, it is easy to define a fraction or a frequency. In an infinite setting, the answer can depend on how one chooses to take limits, which regions one includes first, and how one weights them. Cosmology wrestles with this measure problem in scenarios where inflation produces endlessly many expanding patches in which different outcomes are realized. The probabilities for different observations then depend on a prescription for counting and weighting those patches. There is no universally accepted solution, and reasonable proposals can disagree. This is not a sign that the science collapses in confusion. It is a sign that probability in infinite settings is delicate, and that empirical work must focus on quantities insensitive to such prescriptions, or on developing methods that tie a particular prescription to observable structure. The same care appears when people consider whether an infinite universe inevitably contains the bizarre. If every allowed configuration occurs, then arrangements we would call freakish, fluctuations that assemble complex structures out of randomness, for example, should exist somewhere. Thought experiments about observers who fluctuate briefly out of equilibrium appear in that line of reasoning. These concerns rely on extrapolating statistical mechanics and quantum field behavior into regimes far from what we can test. They may be telling us more about how not to do probability in an infinite setting than about what actually exists in the cosmos. Here, too, infinity is a warning. Do not push familiar intuitions past the conditions under which they were earned. In practice, the decision between spatially infinite and very large finite models is made at the interface where observation meets theory. Astronomers measure correlations in the cosmic microwave background across wide angles, map the three-dimensional distribution of galaxies, and infer geometry from how characteristic length scales are projected on the sky. Theoretical models convert those observables into constraints on curvature and on the size of any fundamental domain. So far, the data are consistent with a universe that is spatially flat on large scales and either infinite or finite with a closure scale beyond what we can currently probe. The situation is a reminder that science often answers grand questions with inequalities, at least this big, within this error, under these assumptions. Infinity remains a live option, not because we like the romance of boundlessness, but because nothing we have measured forbids it, and much of what we think we know about the early universe would make it natural. For everyday life, none of this alters the familiar. The distances between neighboring galaxies are measured in millions of light years, between clusters in hundreds of millions, and the local web looks the same whether there are 10 such filaments in all or uncountably many. Infinity is not an extra glow in the night sky or a vertigo you feel while walking. It is a property of the model that becomes relevant when we ask global questions. The total number of galaxies, the eventual fate of distant light, the chance that a distant region encodes a familiar pattern. There is one more layer to the question that belongs less to observation and more to understanding. The philosophical unease of never-ending distance is not a flaw in cosmology. It is a feature of how the human mind relates to unboundedness. Even after you learn that an expanding universe can be flat and infinite without contradicting darkness or stability, even after you accept that outside has no meaning in a model where the expansion is intrinsic, there remains a quiet tension between the finiteness of experience and the unboundedness of the stage. For some, the tension eases when they remember that our theories earn their keep locally and statistically. What we need for prediction is the rule for how neighboring regions interact and how small fluctuations grow, not an inventory of everything that lies beyond the horizon. For others, the tension is the point. It is a motivation to push observations deeper, to build instruments that can see new standard rulers and candles farther back in time, to refine maps of the microwave sky, and to test whether the largest modes we can observe deviate from our simple models. Whether space is infinite or finite but unbounded, the conceptual heart of the matter is the same. In general relativity, there is no edge to run into, no enclosing room, no outer darkness into which galaxies fly. There is geometry governed by dynamics, and there are horizons that track what light can connect. Within that structure, the web of matter organizes itself. The background radiation cools and thins, and the catalog of what we can see grows with time. Infinity, when it appears, is not a claim about our personal reach. It is a statement about the form of the whole. We live in a finite window of a possibly boundless expanse, building careful knowledge from signals that arrive after long journeys. If the road of distance never ends, the meaning is not that we are lost in it, but that there is always more to find, and that our small circle of light can keep widening without ever exhausting the night. Chapter 6. Infinite Time, Eternity, and the Arrow of Time. Time is the dimension in which change becomes legible. We picture it as a current carrying moments from a hidden past through a vivid present toward an unopened future. Physics complicates that image in two directions at once. At the level of microscopic laws, many of our best equations are close to time reversal symmetric. If you film a handful of colliding molecules and run the film backward, the equations do not protest. At the level of macroscopic experience, direction is unmistakable. Ice melts but does not spontaneously reassemble. Memories point one way. Causes precede effects. Wrestling with infinity in time means holding both facts together. We have to ask whether time stretches without beginning and without end. And we have to explain how an arrow can be carved out of dynamics that barely notice which way the reel is played. The question of a beginning is where cosmology enters. In general relativity, the universe is modeled as a space-time whose geometry responds to the energy and momentum it contains. Asking whether time had a first moment means tracing typical world lines of particles and of light backward to see whether they extend indefinitely. In the simplest, hot Big Bang models, backward extension runs into a boundary where densities and curvatures become unbounded, and the classical description ceases to apply. That boundary is not a frame in a movie where nothing happens before. It is a signal that the mathematical tools being used have been pushed beyond their domain. A beginning in this sense is the claim that the classical picture cannot be continued farther back along those paths, not yet a claim about what truly exists or happens at that edge. Inflationary cosmology enriches this picture. If the very early universe underwent a brief era of accelerated expansion, then a small, nearly uniform patch could be stretched into a region much larger than our observable domain. Inflation explains the remarkable uniformity of the cosmic microwave background and the almost scale-invariant pattern of the primordial ripples that later grew into galaxies. It also tempts us to think about eternity to the past. Could inflation have been going on forever, with our patch one late bloom in an endless field? An influential obstruction comes from the Bordeguth-Vilenkin theorem. Under broad conditions, if the average expansion rate along some past directed geodesics is positive, those geodesics cannot be continued arbitrarily far into the past. The space-time is past incomplete along them. The theorem does not prove a singularity of infinite curvature, and it does not cover every imaginable cosmology, but it does say that simple eternal inflation cannot be the whole story to the past. Something else, an earlier phase, a bounce, or a new kind of description, must take the baton. Several ideas try to soften or remove a beginning without abandoning the successes of the standard model where it works. Bounce models replace the singular boundary with the transition from contraction to expansion. In loop quantum cosmology, quantum geometric effects expected near the Planck scale can produce an effective repulsion at extreme density, preventing a collapse to zero size and yielding a bounce that connects a prior contracting phase to the expanding universe we inhabit. Ekpyrotic and cyclic scenarios, inspired by higher dimensional theories, imagine brain-like objects approaching and interacting in a way that mimics a hot Big Bang for observers inside. These proposals must navigate tight constraints. They need to generate the observed nearly Gaussian, nearly scale-invariant spectrum of fluctuations. They must remain stable against growth of unwanted inhomogeneities, and they cannot contradict nucleosynthesis, the cosmic microwave background, or the late-time expansion history. None has yet graduated from promising framework to established history, but together they show that a mathematically honest beginning in relativity is not the end of the story. It is a boundary where new physics, or a new representation of old physics, may be required. There is also a conceptual option that rearranges the question completely. Time might be emergent rather than fundamental. In several approaches to quantum gravity, one seeks a timeless underlying description, an equation that does not contain an explicit time parameter, whose solutions can in appropriate regimes be interpreted as evolving spacetimes by observers who carry internal clocks. The analogy is thermodynamic. Temperature is not inscribed on individual molecules. It emerges as an effective property for large collections. Likewise, before and after might be relational features born when many degrees of freedom cohere into a semi-classical world. In such a view, asking whether time extends infinitely into the past may be like asking whether temperature existed before a gas formed. The question belongs to one level of description and may lose its grip at another. That is not a license for obscurity. It is a reminder that the language of duration could be approximate, and that beginning might be a statement about when a particular description became valid rather than about an absolute first tick. If the past presents one kind of infinity, the future presents another, and here observation and theory combine to yield a relatively sharp forecast. On the largest scales, the expansion of the universe is accelerating. The simplest explanation is a cosmological constant, an energy density associated with empty space that does not dilute as the universe expands. If this picture holds indefinitely, the universe asymptotically approaches a de Sitter-like state, cold, diffuse, and dominated by a horizon. Galaxies not gravitationally bound to ours recede beyond causal contact. The night sky thins as distant systems slip irretrievably away. Within gravitationally bound islands, stars exhaust their nuclear fuel. New star formation dwindles as gas is used up or locked in remnants. White dwarfs cool and fade. Neutron stars and stellar mass black holes persist. Over fantastically long durations, if protons are unstable, ordinary matter decays. Black holes, which store enormous entropy, slowly evaporate by emitting radiation, turning their mass into a faint bath of particles. After the last black hole has evaporated, a de Sitter horizon remains with a small but non-zero temperature associated with its surface gravity. The picture is of an ever-expanding stage on which fewer and fewer dramatic events occur. Heat death is not an instant. It is an approach toward a limit where free energy that can be harnessed to do work becomes vanishingly scarce. Alternative futures exist in theory and are constrained by data. If the agent driving acceleration is not a true cosmological constant, but a field whose pressure is even more negative, expansion can accelerate so violently that it eventually overcomes all binding. Structures are torn apart, then solar systems, then planets, then molecules, and finally even hadrons, in a scenario colorfully called the Big Rip. Current observations place strong limits on such behavior, and the simplest fits to the data favor a cosmological constant rather than this more extreme alternative. But the logical possibility illustrates that the far future is governed by the properties of whatever dominates the energy budget at late times. Another speculative end is vacuum decay. If the state we call empty space is only metastable, quantum tunneling could nucleate a bubble of lower energy vacuum that expands at near light speed, altering constants and particle spectra as it goes. There would be no warning and no survivors, which is why the scenario is a philosophical footnote rather than a practical worry. Between the quiet of heat death and the violence of rips and decays sit gentler, little rip evolutions, in which disassembly proceeds without a finite time singularity. The details differ, but all these futures share a trait. They are scripted by the equation of state of the dominant energy and by how horizons partition what can still influence what. Between the global sketches of beginning and end lies the arrow of time, the asymmetry that imprints direction on our experience. The core of the arrow in physics is thermodynamic. Entropy measures, in a coarse-grained way, how many microscopic arrangements correspond to a macroscopic description. The second law tells us that in an isolated system, entropy tends to increase, not because of a mysterious force pushing it upward, but because low entropy arrangements are special. rare in the space of possibilities, while high-entropy arrangements are typical. A cup shatters because there are vastly more ways to be shards on a floor than intact cup with just these microscopic correlations, and because random molecular jostling does not conspire to rebuild the correlations needed for reassembly. The law is statistical. It does not say entropy can never decrease in a small subsystem over a short time. It says that, given the boundary conditions we actually have, decreases are exceedingly unlikely compared with increases. The arrow is the tendency for typical histories to move from special states to generic ones. Gravity complicates and enriches this story. For gases in a box, the uniform distribution is high entropy. For matter under its own gravity, uniformity can be a low entropy starting point because gravity prefers clumping. Allow a nearly smooth distribution to evolve and small inhomogeneities grow, forming stars, galaxies, and black holes. The entropy associated with gravitational degrees of freedom, especially the entropy attributed to black holes, is immense. In that light, the smoothness of the early universe was not a high-entropy fog that later crystallized. It was extraordinarily low-entropy initial data, with a vast entropy budget left to exploit. The cosmological arrow that points from a hot, dense, nearly homogeneous past to a cooler, clumpier future is the gravitational face of the thermodynamic arrow. The two are not in competition. They are the same narrative told in different dialects. Two classic challenges clarify what this account must accomplish. Loschmidt's reversibility objection notes that if microscopic dynamics are reversible, then for every history in which entropy increases, there exists a history in which entropy decreases. Why do we not witness the latter? The answer is probabilistic and boundary conditioned. Given a low-entropy past, the overwhelming majority of microhistories compatible with that past and with what we see now continue toward higher entropy. The time-reversed histories that take a generic high-entropy state into a delicately tuned low-entropy state exist in principle, but form a set of measure unimaginably small. Poincaré's recurrence observation raises the mirror concern. In a finite, isolated system evolving reversibly, the system will, after a fantastically long time, return arbitrarily close to its initial microstate. Does that not erase the arrow? In practice, the timescales dwarf any physically relevant duration for macroscopic systems, and real systems are never perfectly isolated. More importantly, the statistical reasoning that supports the second law is local in time and conditioned on actual boundary data, not on the behavior over eons in an idealized box. The arrow shows up in other guises that align rather than compete. The electromagnetic arrow appears as our preference for retarded radiation, waves spreading out from charges, over advanced radiation converging upon charges from the future. The local equations permit both kinds of solutions. The selection is effectively enforced by boundary conditions. The universe contains sources that have radiated into an absorptive environment, and not a conspiracy of absorbers focusing coordinated advanced waves into every antenna. The radiative arrow is a corollary of the thermodynamic one. The psychological arrow, by which we remember the past and anticipate the future, piggybacks on entropy as well. Memory storage requires physical records. Record formation increases entropy somewhere. Agents capable of prediction are those capable of exploiting reliable coarse-grained regularities, and those regularities are built from a past in which correlations were set and a future in which they have not yet been scrambled. Quantum mechanics adds texture without dismantling the picture. In textbook language, measurements collapse a spread of possibilities into definite outcomes, injecting irreversibility where the Schrödinger equation by itself has none. In interpretations where no fundamental collapse occurs and the dynamics are strictly unitary, the apparent arrow emerges from decoherence. Interactions with an environment entangle a system's phases with many uncontrolled degrees of freedom, effectively suppressing interference between alternative histories. Once information about a system has leaked into vast environmental registers, reversing the entanglement to recover coherence would require concerted manipulations beyond practical reach. In either reading, the empirical arrow is traced back to special boundary data and the practical impossibility of reconstructing microscopic correlations. All arrows eventually point to one stubborn fact: the early universe was special. It was hot but extraordinarily uniform on large scales, with tiny fluctuations imprinted in the primordial radiation that later seeded structure. The near isotropy of the microwave background encodes that smoothness to high precision. Inflationary models explain several aspects of this initial simplicity by stretching a small, nearly uniform patch into a vast region and diluting unwanted relics, and they account for the pattern of primordial fluctuations observed. But even inflation does not by itself eliminate the need for a low-entropy condition. A central task for fundamental cosmology is to explain why this smoothness held, or to show that, in a deeper theory, smooth initial data are typical once the right variables are used. This is sometimes called the past hypothesis, a simple statement that the universe began in a low-entropy macro state. It is not yet derived from deeper principles, but it is consistent with everything we measure, and it is enough to anchor the second law, the radiative preference, and the psychological direction in one coherent account. If time is infinite to the future in a de Sitter-like state, a new puzzle arises from the combination of horizon thermality and boundless duration. Quantum fluctuations in a thermal background can, in principle, occasionally assemble organized subsystems. Over stupendous spans, one might worry that such Boltzmann brain observers would vastly outnumber observers who arise from long evolutionary histories like ours. Most researchers treat that conclusion as a reductio. A cosmological model that predicts typical observers who are isolated, short-lived fluctuations rather than products of a long arrow-respecting history is presumed to be missing a piece, either because the measure used to count observations is ill-posed in an infinite setting, or because a correct theory of late-time physics eliminates the conditions required for such fluctuations to dominate. The issue is not an empirical threat. It is a consistency test for how we use probability in an eternal future. Eternity is a word that enters here from outside physics and refuses to stay outside. In many strands of classical theism, eternity names not an infinite sequence of days, but an atemporal mode of existence in which all times are present in a single, unified vision. Augustine described the divine as outside time, not wading through ages, but encompassing them. Boethius called eternity the whole, perfect possession of endless life all at once. Philosophers have debated whether only the present is real, presentism, whether past, present, and future are equally real, eternalism, or whether reality grows as new events occur, the growing block view. Physics does not adjudicate these metaphysical stances, but it gives them a stage. In relativity, different observers slice space-time into nows differently. Simultaneity is not absolute. That feature tilts the playing field away from naive presentism and toward block-like pictures. Yet the felt flow and the thermodynamic arrow demand explanation within any metaphysics. Religious traditions that emphasize cycles, creation, dissolution, rebirth, cast eternity as recurrence rather than as a temporality. Those motifs rhyme with scientific cycles loosely, but the match is poetic rather than predictive. The prospect of infinite time in either direction naturally produces unease. A past that never began threatens to dissolve explanation into an endless chain. A past that began at an opaque boundary invites a different discomfort because it seems to ask for a cause when before may have no purchase. A future that never ends raises questions about value and meaning in the face of heat death, repetition, or decay. A future that ends abruptly in a rip, crunch, or vacuum transition can feel harsh. Physics cannot prescribe comfort, but it can clarify the terrain. Observations point to a hot, dense early phase followed by expansion. They point to a low entropy beginning relative to what gravity allows. They point to late time acceleration. Within that map, the arrow becomes intelligible as a consequence of boundary conditions and statistical typicality, and eternity becomes a question about extrapolations that we can label by their assumptions and test where possible. If time has neither edge nor final harbor, our task is not to arrive, but to understand the currents, and the arrow we feel is how understanding keeps its bearings. If time began or will end, that does not shrink what we are, because the present is where the universe becomes real for us, and in that meeting there is always enough depth to explore. Chapter 7. Infinity in Quantum Physics. Quantum theory confronted infinity not as a distant philosophical horizon, but as an immediate technical obstruction. The earliest quantum field theories were built to describe charged particles and the electromagnetic field as dynamical degrees of freedom that interact and create one another. The framework was natural. Take the classical field equations, elevate fields to operators, impose commutation relations, and compute scattering probabilities by expanding in powers of the coupling. The surprises began as soon as one asked for numbers. Loop corrections in the perturbation series, terms that reflect the fact that fields interact with their own fluctuations, produced integrals that diverged when the momenta circulating in the loops were set to arbitrarily large values. The electron's self-energy correction, for example, did not settle to a finite shift. It grew without limit as higher and higher virtual momenta were included. Vacuum polarization, in which the electromagnetic field momentarily produces particle-antiparticle pairs, altered the effective charge seen at a given distance, but the underlying integrals were again ultraviolet divergent. The energy density of the vacuum itself, obtained by summing the zero-point energies of all field modes, was, in the naive implementation, infinite. These were not rarities, they were systematic. The nascent theory seemed to insist that nature hides an infinity at every turn. The first response was not to deny the infinities, but to bracket them. Practitioners inserted a cutoff, an artificial boundary that limited how high a momentum could run in the loops, and they discovered a pattern. The divergent parts of the amplitudes had the same mathematical form as terms already present in the Lagrangian, the concise encapsulation of the theory's dynamics. One could absorb the infinities into a redefinition of a few parameters: the mass and charge of the electron, the normalization of the field, and similar constants for other fields. After this renormalization, the predictions for observables, differences between quantities, cross-sections for particular reactions, shifts in energy levels, became finite and well-defined. That maneuver would have deserved suspicion if it had been merely cosmetic. It was not. The finite parts of the renormalized predictions could be tested, and they worked with astonishing accuracy. The anomalous magnetic moment of the electron, predicted by quantum electrodynamics with renormalization in place, matches measurement to many significant figures. The Lamb shift in hydrogen, the small splitting of energy levels that are degenerate in the simplest Dirac theory, finds its explanation in radiative corrections that require renormalization to tame their infinities. A procedure born in embarrassment became a tool of precision. Renormalization at first looked like a technical fix. Redefine parameters to cancel infinity against infinity and move on. The deeper understanding came later. The question was why the fix worked here and not everywhere, and what the presence of divergences meant about the theory's domain of validity. A criterion emerged. Interactions are organized by how their strengths scale when one changes the resolution at which a system is examined. If an interaction grows stronger at shorter distances in such a way that new independent parameters are needed at every step, the theory would lose predictivity. Infinitely many measurements would be required to fix those parameters. If, on the other hand, only a finite set of parameters must be adjusted as the resolution changes, then the theory is renormalizable and remains predictive once those few are fixed. Quantum electrodynamics belongs to the latter class. The infinities can be swept into a redefinition of a finite small set, and all other consequences follow. This classification, which began as a power-counting exercise in the hands of Dyson and others, was elevated into a general philosophy by the renormalization group. Do not think of a theory as defined at a single scale. Think of it as living on a flow that relates descriptions at different scales. The renormalization group reorganized infinity into insight. In this view, one systematically integrates out fluctuations above a certain momentum scale, obtaining an effective theory for the longer distance modes that remain. The parameters in the effective theory run with the scale. The coupling that governs interactions at one resolution is different from the coupling that governs them at another. The crucial fact is that many microscopic details of the high-energy theory are irrelevant for long-distance behavior. Different microscopic theories can flow toward the same effective description. The buzzword for this is universality, and it explains why critical phenomena in magnets and fluids share exponents even when their microphysics differ. The same mathematics that tells a condensed matter physicist how vortices proliferate in a thin superfluid film tells a high-energy physicist how interactions evolve as one probes shorter distances. In both domains, fixed points of the flow, places where the parameters stop running, organize behavior across scales. Near certain fixed points, theories are predictive, because departures from the fixed point are controlled by a small number of relevant parameters. Further details wash out. Infinity has been turned from a breakdown into a classifier of behavior. Within this flow-based perspective, renormalization ceases to look like a dodge. It encodes the fact that any measurement is performed at finite resolution, and that the numbers we call mass and charge are not properties of isolated particles in the abstract, but manifestations of how a field responds at a given scale. Screening by vacuum polarization makes the electric charge appear larger at shorter distances, a running captured by a renormalization group equation. Anti-screening in non-abelian gauge theories makes the strong interaction weaker at high energies, a phenomenon called asymptotic freedom. The latter discovery transformed the understanding of the strong nuclear force. Quantum chromodynamics, the theory of quarks and gluons, is a gauge theory whose coupling decreases logarithmically with increasing momentum transfer. At very short distances, the force becomes weak, and quarks behave almost as free particles. At longer distances, The coupling grows and quarks are confined into hadrons. The same mathematics that quantifies the divergent loop integrals explains why one can do high-precision calculations in processes with large momentum transfer while requiring non-perturbative methods, such as lattice simulations, to capture long-distance phenomena like hadron masses and confinement. Infinity marks the limits of one computational method and points to the other method that must take over. It would be misleading to pretend that renormalization is only about ultraviolet short-distance infinities. Infrared divergences, those that come from contributions of arbitrarily long wavelength quanta, also appear. In quantum electrodynamics, for instance, idealized scattering amplitudes diverge because processes with the emission of soft photons are indistinguishable, in practice, from the same processes without that emission. Real detectors have finite energy resolution. Any actual measurement sums over events with and without additional photons below a threshold. When one computes inclusive rates that match this physical situation, the infrared divergences cancel. The theorem that guarantees this cancellation in a broad class of theories ties the resolution of infrared infinities to the way we must phrase empirical questions. In quantum chromodynamics, there are similar subtleties. Collinear divergences arise when particles split into nearly parallel components. The appropriate way to define observables, jet cross-sections for example, again ensures that inclusiveness and factorization combine to yield finite quantities. Infinities here are not mistakes. They are pointers telling us that only properly framed questions deserve answers. The quantum vacuum is the other arena where infinity alternates between problem and instrument. In classical physics, the vacuum is inert, a background of nothing. In quantum field theory, it is the ground state of a system with an infinite number of degrees of freedom. Fields in their ground state still fluctuate. Uncertainty cannot be switched off. A convenient language for these fluctuations uses the notion of virtual particles, excitations that exist not as isolated on-shell quanta with a fixed relation between energy and momentum, but as transient disturbances that mediate interactions in intermediate steps of a calculation. Virtual particles are not particles in the everyday sense. They are bookkeeping devices in perturbation theory, the internal lines in a Feynman diagram, but they leave footprints in observables. Vacuum polarization alters the Coulomb law at short distances. The presence of conducting boundaries changes the allowed modes of the electromagnetic field, and the resulting shift in zero-point energy can be detected as a tiny force, the Casimir effect, between parallel plates. Subtle shifts in atomic energy levels, including the Lamb shift, are explained by the way the fluctuating vacuum modifies the electron's interaction with the nucleus. Even in curved spacetime or in accelerated frames, vacuum fluctuations acquire a new face. An observer with constant acceleration perceives a thermal bath of particles in what an inertial observer calls the vacuum, and black holes radiate because quantum fields near the horizon are entangled in a way that makes empty look different inside from outside. None of these effects requires that the vacuum energy itself be literally infinite. They require careful comparison between configurations where differences are finite and measurable. The formal infinity of the bare vacuum energy is both a technicality to be regulated and, in a different context, the seed of a profound puzzle. That puzzle is the cosmological constant problem. If one sums the zero-point energies of all quantum fields up to a high-energy cutoff, the result is fantastically large. If one couples that naive calculation to gravity, the associated vacuum energy would curve spacetime to an extreme degree. Observations, however, tell us that the acceleration of the universe can be accounted for by an effective vacuum energy that is tiny by comparison, smaller than the naive estimate by many orders of magnitude. The contrast is not a small mismatch. It is a gulf so vast that one is tempted to imagine that the true vacuum energy is exactly zero by some principle that we have not yet found. But the observed acceleration is consistent with a small positive value, and the various known contributions do not seem to cancel naturally to that value. This is not a divergence in the sense of an integral that blows up. It is a failure of our present theories to explain why an apparently natural contribution is absent or superseded by something else. Unlike the ultraviolet infinities that renormalization handles with aplomb, the cosmological constant problem remains an open wound. Infinities appear, too, in subtler guises. Perturbative expansions in quantum field theory typically are not convergent series. They are asymptotic. Their coefficients grow factorially at high order, and summing them term by term is a recipe for instability. Borel summation and related techniques can extract useful information from such series, and the large order behavior carries physical content. Renormalons and instantons, non-perturbative features that tell us about the theory's structure beyond perturbation theory. Here, infinity is not an integral that diverges, but a growth in complexity as one asks for more and more precision from a simple expansion scheme. The lesson is the same. Methods have domains. When infinity intrudes, it is not only a warning, it is a map showing where a different method waits. The Goldstone and Higgs mechanisms add a complementary role for infinity as a diagnostic. When symmetries are exact, certain relations among processes hold. When symmetries are broken by dynamics, new degrees of freedom appear, such as nearly massless excitations associated with the breaking. Quantum corrections, however, are sensitive to high-energy behavior. Scalar particle masses, in particular, receive additive contributions that scale with the cutoff. In a theory where the Higgs boson is elementary and the relevant high-energy cutoff is very high, keeping its mass small appears to require delicate adjustments of parameters, a fine-tuning that some take as an aesthetic alarm. This is the hierarchy problem, not an infinity, but an unnatural sensitivity to where one stops the integral. Decades of model building have explored ways to soften this sensitivity. New symmetries that protect masses, new strong dynamics that replace scalars with composites, extra dimensions in which the bookkeeping of contributions is altered. The data so far constrain many of these ideas, and it is possible that nature simply does not share our aesthetic discomfort. But the discomfort was born from the same encounter with infinity. Integrals that reach into the ultraviolet and ask the low-energy world to balance what the high-energy world provides. Beyond the standard model, new examples proliferate. Gravity, when quantized in the same manner as other fields, looks non-renormalizable by the old criterion. Its coupling grows with energy in a way that demands new counterterms at each order. As an effective field theory, however, quantum general relativity works beautifully at low energies, where only a few terms are needed and their coefficients can be fixed by measurements. At high energies, something else must take over. It could be an ultraviolet completion in which gravity becomes finite by new degrees of freedom, strings rather than points, or it could be an asymptotically safe fixed point where the flow of couplings tames itself. In both approaches, infinity is a target to be managed, not a calamity to be avoided. One either replaces point-like interactions by extended ones, smearing the integrals that diverge, or one discovers that the flow reads just so that no divergence remains at the end of the day. The debate is ongoing, and observations at accessible energies are only weakly informative. The thread that ties the stories together is the ubiquity of the renormalization group viewpoint. It is the language in which these proposals are stated and judged. It is worth pausing to ask why the language of virtual particles persists when we know that a better, more global picture exists. The path integral formulation, in which one sums over all field configurations weighted by a phase determined by the action, seems to banish the little messengers from the narrative. Yet even there, the same integrals appear, the same ultraviolet sensitivity has to be regulated, and the same running of couplings emerges. Virtual particles are provisional creatures, but they organize the calculational world cleanly, especially when the coupling is small enough that expansions in the number of loops make sense. When one leaves perturbation theory, other images take over. Condensates that pervade the vacuum in broken symmetry phases, topological sectors labeled by winding numbers, instantons that control tunneling. In all cases, the infinity of possibilities, the fact that one sums over more than can ever be enumerated, is not a bug. It is the essence of the quantum field. The trick is to ask questions for which that essence can be coerced into finite, testable answers. There is a physical regulator, too, that is conceptually clean, even if it is computationally heavy. Lattice field theory places space on a grid with finite spacing and replaces integrals by sums. The lattice spacing is a cutoff that removes ultraviolet infinities by construction. One then takes the spacing toward zero, approaching the continuum limit in a controlled way. For quantum chromodynamics, lattice simulations have delivered hadron masses and low-energy constants with steadily increasing precision. The lattice also reminds us of the Wilsonian picture. A continuum limit is approached by tuning parameters toward a critical point where the correlation length in lattice units diverges. Infinity reappears as the signpost that one has reached the physics that does not care about the details of the regulator. Sometimes infinity constrains theory so sharply that only narrow combinations of ideas survive. Gauge anomalies, quantum violations of classical symmetries, arise from subtle ultraviolet effects in loop diagrams, and their cancellation is required for consistency. The matter content of the standard model is placed just so that anomalies cancel. Change the charges or the representations, and the theory would fail. Here infinity manifests not as a number, but as a logical sieve. Only anomaly-free combinations flow to well-defined quantum theories. Such constraints are among the reasons that model building beyond the standard model is tightly choreographed. Not every imaginative extension survives passage through the sieve. The impression that emerges from this long encounter is that infinity in quantum physics is both a problem and a tool. It is a problem because naive calculations blow up, because predictions should be finite, and because some extrapolations of known ideas fail spectacularly when the integrals are taken seriously. It is a tool because the manner of divergence encodes how a theory perceives scale, because the flows it induces organize the relationships between phenomena at different energies, because its cancellation enforces deep consistency conditions, and because regularization methods that make it explicit preserve symmetries we need for physical answers. Dimensional regularization, for example, analytically continues the number of space-time dimensions away from 4, computes integrals where they converge, and then returns to 4 dimensions, extracting poles whose residues are universal. The method is not an aesthetic curiosity. It is valued because it respects gauge invariance and thus maintains the delicate cancellations on which physical amplitudes depend. Infinities, revealed and corralled, become the scaffolding on which the finite building stands. If there is a single moral to carry forward, it is that quantum field theory never promised to be a description of everything at all scales. It promised to be systematic within a window. Effective field theory codifies this promise. One writes all interactions permitted by the symmetries, organizes them by how they scale with energy, and truncates at an order sufficient for the desired precision. The predictive power comes not from a denial of fields beyond the window, but from the knowledge that their influence is suppressed by powers of the high scale. Infinity is domesticated not by banning it, but by quantifying how its fingerprints fade as attention shifts to the slow modes, the long wavelengths, and the accessible energies. This logic unifies nuclear physics, particle physics, and condensed matter. It explains why one can understand the low-energy excitations of a crystal without simulating every electron and nucleus, and why one can calculate a scattering cross-section at a collider without knowing whether gravity is asymptotically safe or strings vibrate in extra dimensions. At the smallest scales we can speak of, the world answers our questions by forcing us to think in an unbounded way and then rewarding us with finite, accurate numbers. If there is a lesson in that, it may be that infinity is not only where understanding fails, it is where our methods learn what they are for. Chapter 8. Infinity and the Multiverse. The word multiverse gathers several different ideas under a single name, and each of those ideas borrows its force from infinity. Sometimes the infinity is spatial, an unending expanse in which regions beyond our horizon play out variations on the same local laws we know. Sometimes it is temporal, a process in the very early universe that does not end everywhere at once and keeps spawning new cosmic domains with altered properties. Sometimes it is quantum, an infinity of branches that appears when the unitary evolution of a wave function is followed through interactions that disperse coherence into the environment. These proposals differ in mechanism and in the kind of evidence one can reasonably demand from them, but they overlap in a central insight. If reality is unbounded in the relevant way, then what we see may be only one of many realized histories rather than the whole. Begin with the most conservative picture: an infinite, statistically uniform space governed by the same local laws that operate here. In such a scenario, the observable universe is only a patch, bounded not by walls, but by the finite time light has had to reach us during cosmic expansion. General relativity ties the geometry of space to its matter content and to the history of that expansion. If space is flat on large scales and does not close on itself by a global identification, the equations do not forbid it from extending without end. Observations of the cosmic microwave background and of the large-scale distribution of galaxies show near flatness and near uniformity over the largest scales we can probe. Those statements do not prove literal infinity. A very large but globally closed space could look the same to us so long as its characteristic closure scale exceeds our horizon. But an infinite option is consistent with what we see, and the physics that fits the data most simply favors a spatially flat geometry in which infinity is a live possibility. Infinity in this simple sense has consequences that are startling even without changing any laws. Any finite region contains only a finite amount of information when described at a limited resolution. Devices that record facts have finite capacity. Brains, disks, and spin registers do not store unbounded detail. If the whole of space contains infinitely many such regions, and if the statistics of local configurations are stationary, then every allowed arrangement is realized somewhere, and in fact realized infinitely many times. That conclusion depends on a modest finiteness assumption about local state space. At a coarse-grained level, the assumption is natural. In a Hubble-sized volume, at a fixed cosmic time, the energy is finite, the entropy is finite, and the number of macroscopically distinguishable states is correspondingly finite. One does not need an exact count for the conclusion to hold, only the recognition that when a finite set of possibilities is sampled infinitely often, repeats are guaranteed. The distances between repeats would be fantastically large, far beyond anything that could matter observationally. But the logic is crisp. In an infinite stadium with finitely many seat types, seats repeat. Inflationary cosmology adds a second layer to this spatial picture. Inflation is the idea that the very early universe experienced a burst of accelerated expansion driven by the potential energy of a field. That expansion smooths and flattens any initial irregularities within a patch, explaining the remarkable uniformity of the microwave background and diluting unwanted relics. Quantum fluctuations of the inflaton field are stretched by the rapid expansion and frozen as classical perturbations. Those tiny variations seed the density ripples that later grew under gravity into galaxies and clusters. Inflation is not merely a hand-waving story. It yields specific predictions about the statistical character of the primordial fluctuations, near-scale invariance, near Gaussianity, and adiabaticity, and those predictions match what we infer from the microwave sky and from the galaxy distribution to high precision. In many models, the inflationary process does not end everywhere at once. The inflaton field rolls down its potential in a quantum noisy way. In some regions, it decays and reheats, producing a hot Big Bang like the one that preceded our observable history. In other regions, it lingers at higher potential energy and continues to drive accelerated expansion. New pockets are continually butted off from this inflating background, and each pocket undergoes its own hot, dense beginning, cools, and forms structure. This is eternal inflation. It is not eternal into the past under broad conditions, but it can be eternal to the future, producing an unbounded ensemble of causally isolated domains. If the underlying particle physics admits multiple low-energy phases, many local minima in a multidimensional potential, then different pockets can cool into different vacua. The patterns of symmetry breaking may select one set of particle masses and force strengths in one pocket and a different set in another. The effective cosmological constant may take different values, large and positive in some domains, near zero in others, perhaps even negative in others. In such a picture, our measured constants are environmental. One draw from a distribution over domains rather than unique outputs dictated by a single dynamical law. That shift in explanatory mode is not a license to say anything goes. It replaces the task, derive the constants with a different task, characterize the ensemble of pockets, compute the distribution over vacua, and condition that distribution on whatever minimal requirements our kind of structure imposes. That program faces two difficulties. First, we do not yet know enough about the high-energy theory that would underwrite the landscape of low-energy vacua. Second, eternal inflation produces infinite numbers of pockets, and comparing infinities calls for a measure, an agreed-upon regularization of how to count that does not spoil local physics or generate paradoxes. Different reasonable prescriptions can yield different relative frequencies for events, a dilemma known as the measure problem. Work continues on measures that weight domains in a way that avoids pathologies and matches what we can test, but no consensus has emerged. In practice, one concentrates on predictions that are relatively insensitive to measure choice and on those aspects of inflation, such as the near-scale invariant spectrum of fluctuations that are tested within our single domain. Testing the level 2 picture directly is subtle because we do not see other pockets. Light from them does not cross the still inflating regions between. Indirect traces are not out of the question. A collision between our pocket and another early in its history could leave a telltale asymmetry in the microwave background, a circular or disc-like imprint, or a distortion in the statistical pattern of fluctuations. Searches for such signatures have been conducted. None has produced a compelling detection. More broadly, the overall logic of inflation is tested every time we measure the spectrum and statistics of primordial fluctuations with greater precision, and every time we place tighter bounds on spatial curvature and on departures from Gaussianity. The case for eternal inflation remains a theoretical extension of a framework that is otherwise deeply entwined with observation, plausible, motivated, and incomplete. Parallel to these cosmological multiplicities sits a different kind of multiplicity in quantum mechanics. The formalism of quantum theory assigns amplitudes to alternative outcomes and evolves those amplitudes unitarily in time. When a system interacts with its environment, phases that would allow interference between macroscopically distinct alternatives are dispersed into the many unmonitored degrees of freedom around it. Decoherence explains why, for all practical purposes, outcomes can be treated as exclusive, even though the underlying evolution is not interrupted by a fundamental collapse. In the Everett or many worlds reading of this formalism, decoherence does not merely justify using classical language. It partitions the universal wave function into effectively autonomous branches, each recording a definite macroscopic history. All outcomes that have non-zero amplitude occur, but they occur on different branches that no longer interfere. Whether Everettian multiplicity is real or a calculational convenience depends on what one demands from a physical theory. The empirical content is delicate. In a strictly unitary dynamics, the standard Born rule that assigns probabilities equal to squared amplitudes is not an extra postulate. It must be justified from the structure of branching and from rational constraints on agents embedded within branches. Arguments from symmetry, typicality, and decision theory have been developed to show how the Born weights emerge as the unique, consistent guide to credences for such agents. Not all physicists and philosophers find those arguments decisive, but they demonstrate that the many worlds picture is not empty rhetoric. It is an attempt to take the equations at face value and to derive observed stochasticity from deterministic branching plus self-locating uncertainty. Crucially, this level 3 multiplicity is independent of level 1 spatial infinity and of level 2 pocket production. A universe could be spatially finite and still branch quantum mechanically. A universe could be spatially infinite and yet undergo a genuine collapse in measurements. Eternal inflation could generate many pockets even if quantum mechanics were supplemented by a single world collapse postulate. If all three mechanisms operate together, the menu of realized histories becomes staggeringly large. If only one or two operate, multiplicity remains but with different scope. Repetition returns as a test of intuition in the spatially infinite picture. The claim that sufficiently large spatial infinity forces the existence of copies of you rests on a finiteness assumption about local state space. At a coarse-grained level, that assumption is plausible, but at a perfectly microscopic level, it needs qualification. In quantum field theory, the Hilbert space of a region is infinite dimensional. When gravity is taken seriously, however, hints from black hole thermodynamics suggest that the number of independent degrees of freedom that can be packed into a region bounded by a horizon is finite and scales with the area of that boundary. Even without leaning on such deep conjectures, the practical point remains. For any fixed resolution at which records can be stored and recalled, there are only finitely many macroscopically distinct biographies a Hubble-sized region can instantiate. If space is infinite, repeats follow. They are not accessible to observation or to communication. They are separated from us by distances that grow with time and are bounded behind horizons we will never cross. The statement is not fanciful. It is a sober combinatorial consequence of unbounded extent plus bounded local description. What can be tested across these ideas? Geometry remains the cleanest handle. Measurements of spatial curvature, the statistical pattern of the microwave background, and the distribution of galaxies constrain how close to flat the universe is on large scales, and whether simple global identifications would leave repeating patterns in the sky. To date, we see near flatness and no matched circles or other convincing topology signatures, which pushes any closure scale, if space is finite but unbounded, beyond our current horizon. Inflation is tested by the near scale invariant spectrum of fluctuations, and by tight limits on primordial non-Gaussianity and on the tensor modes that would betray very high energy scales in the early universe. Many worlds, taken as a literal description, does not produce new laboratory predictions beyond those of standard quantum theory, because it is an interpretation of the same underlying formalism. What it offers is a coherent story for why measurement outcomes look definite, and why the Born rule governs frequencies without adding a collapse postulate. The slogan that every possibility exists somewhere is often used loosely. Physics deals in dynamical possibility, not in unconstrained logical conceivability. In a spatially infinite level 1 setting, every possibility means every arrangement consistent with the local laws and with conserved quantities in a region. In a level 2 setting, every possibility means every low-energy realization that the underlying high-energy theory and the inflationary dynamics actually populate with non-zero measure. In a level 3 setting, every possibility means every outcome to which the wave function assigns non-zero amplitude in a given experimental context, with branches weighted by squared amplitude and rendered non-interfering by decoherence. These are different senses of exists, and conflating them blurs where evidence is available and where it is not. Identity and meaning inevitably enter this territory. Suppose spatial infinity and repetition hold, or suppose the wave function branches into histories that are macroscopically indistinguishable for long stretches. In what sense are the other copies you? In everyday life, personal identity rides on memory links, continuity of brain states, and the social fabric that recognizes a person as persisting. From that starting point, distant copies with identical macroscopic biographies are best thought of as numerically distinct individuals who happen to share a structure, not as a single self stretched across space. In a branching quantum world, branch relatives who share your past up to the moment of decoherence but not your specific outcome are again numerically distinct observers. The most one can say is that before the branching one had self-locating uncertainty about which copy one would become, and that rational credences track the born weights. None of this rescues or erases meaning. Ethics and attachment are local practices. They are not diluted by what distant regions or branches do. Because the multiverse gathers ideas from different parts of physics, it also gathers their cautions. The measure problem in eternal inflation reminds us that probability in infinite ensembles is delicate, and that apparently obvious counting choices can lead to paradoxes if they are not made carefully. The independence of certain mathematical statements about infinite sets offers a distant analogy. Some questions about very large structures may not be settled by the axioms one starts with. The use of anthropic arguments comes with the duty to specify exactly which ensemble they range over and which priors they assume. An anthropic claim that we should expect to see value x because observers are common where x holds is only as good as its accounting of where observers are actually possible and how regions are weighted. There are places where such reasoning seems unavoidable. Accounts of the small but non-zero observed vacuum energy are difficult to make without appealing to selection effects across an ensemble, and places where the same style of argument would be a distraction from the search for a genuine dynamical explanation. The healthiest posture is pluralistic. Use selection when the ensemble is well motivated and no sharper prediction is in reach, and keep looking for dynamics that reduce or eliminate the need for selection. Viewed with generosity, the multiverse is not an escape from explanation, but a new shape of explanation. A single value of a constant can be fixed by a unique dynamical law. A distribution of values across regions can be fixed by a higher-level law about how regions are populated. A single outcome in the laboratory can be explained by a stochastic collapse rule. A distribution of outcomes can be explained by branch weights and decision-theoretic typicality. These shifts carry costs. They trade simplicity of ontology for breadth of account, and they demand a careful separation between what is empirically constrained and what is an inference to the best explanation within a larger scheme. But they also carry an honest lesson about infinity. When the stage is unbounded, some questions change form. Why this value? Becomes why this value in our domain, given the distribution? Why this outcome becomes why this outcome for us, given the weights? The answers are still scientific insofar as they lead to successful conditional predictions and stay anchored to dynamics we can check. If there is a risk in the whole discussion, it is that the word multiverse becomes a talisman that shuts down the impulse to model. That risk is avoidable. Demanding precise statements about what varies, what is held fixed, how counts are performed, and what conditionalizations are used keeps the concept honest. So does tolerating the answer, we do not know, where the theory is not yet specific. The history of physics is full of ideas that began as bold sketches and then either settled into rigor or receded into the background once a better framework arrived. The fate of multiverse ideas will be decided the same way. They will either continue to organize fruitful questions about the early universe and quantum foundations, or they will be reshaped by new principles that make the old taxonomies feel quaint. Either way, the attempt to reason clearly about infinity leaves our concepts sharper than it found them. The unsettling thought of infinite versions of you is, at base, a mirror of the unsettling thought of infinity itself. It places the finite story you live within an ensemble so large that copies and near copies are unavoidable, whether across space in an unbounded cosmos, across branches in a unitary quantum world, or across bubbles in an eternally inflating background. That thought can hollow meaning or enlarge it. It can make choices feel small because they are duplicated, or serious because they are the only ones that will ever be yours. The science does not tell you how to feel. It tells you which sentences about abundance are justified and which are not. If reality is larger than a single world, our task is not to claim all of it, but to understand the piece we can touch and to recognize the conditions under which our piece is one of many. If there are others like us in ways that matter, their existence neither saves nor threatens ours. It only widens the sky in which we think. Chapter 9. The Paradox of Everything. Can infinity be real? To ask whether infinity is real is to stand with one foot in mathematics and the other in physics, and to feel the ground tug in different directions. Mathematics offers precise ways to talk about the unbounded, sets too large to list, sequences with no last term, spaces whose points can be split and split again without reaching a final grain. Physics offers disciplined contact with the world, measurements that return finite numbers, instruments with finite resolution, theories that succeed by taking limits but that deliver predictions we can check. The paradox begins when we try to reconcile these stances. If mathematics can describe actual infinities coherently, why should the world not contain any? If physics must handle only what can be observed, what does it mean to say that space is truly infinite or that time truly has no end? These are not merely verbal puzzles. They probe how models relate to reality and whether the most powerful idealizations we possess are portraits of the world or tools that work because they overreach. There are straightforward arguments that invite us to treat infinity as part of the furniture of nature. Cosmology accommodates spatial slices that are flat and globally unbounded, and our best measurements indicate that on the largest observable scales, space is very close to flat. In a flat, simply connected model with no global identifications, space extends without limit. There is no edge to meet and no path that loops around to the starting point. Inflationary dynamics encourage this picture by smoothing any finite patch into near flatness and by making the total volume vastly larger than what we can see, perhaps effectively endless. Even if the global topology closes on itself, the fundamental domain might be so large that for all practical purposes, the cosmos is boundless to any observer. Time, too, can be extended without contradiction. General relativity allows worldlines that carry on indefinitely into the future. Microscopic laws, quantum field equations in curved spacetime, the local conservation rules that govern interactions, do not insert a built-in last tick. If a model can be continued, why not suppose the world follows it? There is also an argument from the success of idealization. The continuum is woven through physics. The differential equations of fluid dynamics, elasticity, electromagnetism, and quantum mechanics are written on continuous spaces with quantities that vary smoothly and can be probed in the model at arbitrarily fine resolution. Those equations would not work as they do without the infinite divisibility that their mathematics assumes. Calculus, which rests on limits taken through infinitely many refinements, is the language of change in every successful theory since Newton. Quantum field theory, our most accurate framework for non-gravitational forces, represents fields as collections of modes labeled by continuous momenta. Its predictions rely on handling an unbounded tower of fluctuations and then renormalizing the results. Statistical mechanics, which underwrites thermodynamics, treats systems in the thermodynamic limit of infinite volume or infinite particle number to make phase transitions sharp and to derive equations of state. In each case, infinity is not a garnish. It is built into the model at a foundational level, and the payoff is empirical success. It is natural to suspect that what works so well is not a mere trick, that the world's deep structure might itself be continuous and unbounded. Philosophy adds a different support, the indispensability line of thought. If our best scientific theories require mathematics that quantifies over infinite structures, and if we have reason to believe those theories, then we have reason, perhaps defeasible, but reason, to accept the existence of the mathematical entities they quantify over. The claim is not that electrons confirm transfinite cardinals. It is that the continuity and uncountability that enter our explanations are not arbitrary ornaments, but parts of explanations that cannot easily be replaced without sacrificing power and simplicity. On this view, actual infinities in mathematics have earned a kind of ontological credit by doing explanatory work in science. To deny that the world contains anything corresponding to them, or that the mathematics they use refers to anything, would be to make scientific explanation miraculous. Against these invitations stand reasons to be cautious. Every measurement returns a finite amount of information. Instruments have apertures, detectors saturate, clocks tick in discrete counts, and uncertainty relations impose limits on what can be known together. Even before quantum theory, measurement was always coarse. With quantum theory and gravity in play, there are deeper bounds. In a region bounded by a surface, the amount of information that can be stored without collapsing into a black hole is finite and scales with the area, not the volume of the boundary. The Bekenstein-Hawking formula for black hole entropy, along with the broader holographic principle that many take from it, suggests that the independent degrees of freedom in any finite region are bounded in a way that makes the continuum look like an overcounting. If finite areas cap information, no finite laboratory can certify true infinite divisibility, and any talk of uncountably many independent field degrees of freedom in a box looks like a bookkeeping convenience rather than a literal census of nature. Quantum gravity proposals lean in the same direction. Looped quantum gravity predicts discrete spectra for geometric quantities such as area and volume. Space-time, on that picture, is granular at the Planck scale. Causal set theory replaces the continuous manifold by a partially ordered set of events with a fundamental discreteness built in. String theory, while formulated on continuous backgrounds in most of its practical constructions, replaces point particles by extended objects, softening ultraviolet behavior in ways that make a continuum description less urgent at very short distances. Lattice field theory, although employed as a computational regulator rather than as a fundamental ontology, repeatedly shows how discrete scaffolding can be removed by taking a limit in which certain correlation lengths diverge, yielding a continuum as an emergent description with universal features that do not depend on the details of the grid. All of these strands point to a possibility that is coherent and serious. The continuum may be an effective language, not the last word. An actual infinity might never be realized in the world's inventory of independent facts. Physics also distinguishes sharply between infinities that signal real structure and infinities that signal a breakdown. Singularities in classical general relativity are places where curvature invariants blow up and geodesics cannot be extended. Most physicists take these divergences not as indicators that spacetime literally acquires infinite curvature, but as signs that the classical theory is being asked to do work at scales where quantum gravity is required. Ultraviolet divergences in quantum field theory are tamed by renormalization, the running of couplings that results as a discovery about how physics organizes by scale but the bare infinities themselves are not directly measured. Infrared divergences are cured when one phrases questions in inclusive, detector-appropriate ways. These examples share a moral. When infinities appear in calculation, their role is diagnostic. Some are structural, pointing to universal behavior. Others announce that a model has been pushed beyond its domain, or that a question has been asked in an ill-posed way. To infer from infinity in an equation to infinity in the world is to skip over the hard work of interpretation. The classical philosophical divide between potential and actual infinity returns here with practical force. Potential infinity is the idea of a process that can be extended without end, counting, refining, iterating. Actual infinity is a completed totality that contains infinitely many elements at once. Much of physics thrives on potential infinity. We take a limit of finer and finer partitions to define a derivative. We let observation times grow to extract narrow spectral lines. We consider larger and larger volumes to define intensive quantities. In each case, the infinite is a method. Whether the world contains completed infinities, a spatial slice with truly infinite volume, a temporal history with a truly infinite past, a field with uncountably many independent local degrees of freedom, is a separate and far more delicate proposition. It is not defeated by appeal to finite instruments alone, but it is not settled by the success of taking limits either. Could infinity itself be an illusion born of perspective? There are several ways to make that suspicion precise. One is operational. Horizons limit what any observer can see. A cosmological horizon in an accelerating universe hides regions forever. A black hole horizon hides interiors. If the claim that space is infinite amounts for any observer to a claim about regions beyond all possible contact, it is reasonable to ask whether such a claim is something physics is licensed to make, or whether it is a promissory note we carry because our equations extend smoothly. Another is epistemic. The continuum often arises when we discard details. In thermodynamics, continuity and differentiability describe averages over many microstates. The infinite volume limit sharpens phase transitions that are rounded in finite systems. In fluid dynamics, the continuum ignores molecules and treats density and velocity as fields. The derivations that justify this procedure require scales on which mean free paths are small compared with the variations we track. In solid-state physics, band structures are computed in periodic continua that ignore atomic granularity at a deeper level. The fact that these continuums work so well does not make them literal inventories of the world. It makes them superbly calibrated illusions, like the smoothness of a table that is, under magnification, a mosaic of peaks and valleys. A stronger version of the same point appears in the way large numbers enter explanations. The second law of thermodynamics is about typical behavior in spaces of possibilities so enormous that recurrence times dwarf any conceivable duration. We use infinite time as a shorthand for longer than any time relevant to the system, not as a metaphysical claim about eternity. The thermodynamic limit is a technique for turning steep but finite crossovers into mathematically crisp phase transitions. It trades unmanageable complexity for clean language. In high-energy theory, large N limits study gauge theories by sending the number of colors to infinity. The technique reveals structures that are otherwise obscure and often survives in its predictions when N is returned to its real-world value. In each case, infinity is an instrument that refracts complicated finitude into something tractable. The risk is to forget that the instrument is an approximation. Yet there are places where banishing infinity as an illusion would cost us more than it saves. The countable-uncountable divide in mathematics leads to theorems that control which proof techniques work and which fail, and those theorems spill into analysis and topology in ways physics uses every day. The classification of critical phenomena by renormalization group fixed points depends on a scale-free picture that is, in the mathematics, expressed with true limits. The very idea that a theory can be universal at long distances, insensitive to most microscopic details, is a statement about flows approaching domains that are defined by infinite processes. Even if the world never hosts an actual infinity of scales, it can behave as if it does over ranges wide enough that the infinite idealization earns its keep. The question, is infinity real? Therefore bifurcates. It is perfectly sensible to say that certain infinite structures are real in mathematics because their properties can be stated and proved and their relationships mapped, and also to say that physics uses those structures because they organize phenomena, even if, in the world, those structures are not literally instantiated. Where, then, is the fine line between mathematics and physical reality? It runs through the act of modeling. Mathematics supplies a vast library of possible structures. Physics selects some, interprets their symbols as measured quantities, and constrains them with data. The selected structures almost always contain idealizations that are not literally true. Perfectly rigid bodies, perfectly incompressible fluids, point charges, frictionless planes, infinities of extent. We keep the idealizations because they make predictions simple and because the corrections to them can be kept track of when needed. The success of a model does not certify all of its assumptions as facts. It certifies the model as adequate within a domain. It is tempting to elevate adequacy to ontology, to say that because a continuum model works, nature is a continuum, or that because a calculation sums modes to infinite momentum, those modes exist. A more cautious attitude treats success as permission to use the structure, not as a proof of its literal instantiation. This caution does not collapse into skepticism. Sometimes, physics does convert a model feature into an ontological claim. We no longer say that atoms are convenient fictions. We have imaged their positions and manipulated individual ones. We no longer say that gravitational waves are mere ripples in equations. We have measured their strains as they pass through detectors. The difference is not that atoms and waves are finite. It is that we found independent routes to their detection and wove them into a network of mutually supporting facts. Infinity resists this weaving because its most salient forms lie where observation cannot reach, beyond horizons, below cutoffs, at the ends of limits. That resistance is not decisive. It is a reminder that assertions about actual infinity carry a different burden of proof than assertions about finite detectable entities. So does physics allow actual infinity or only potential infinity? The honest answer is that both attitudes are in play. Many of our best theories are written on continuous manifolds. They permit solutions with spatially infinite slices and temporally unbounded evolutions. They manipulate uncountably many degrees of freedom. Within those theories, actual infinity is permitted and sometimes selected by the simplest global assumptions. At the same time, the most disciplined use of those theories treats infinity operationally. We compute differences that are finite, we renormalize divergences, we take limits after framing questions in experimentally honest ways, and we treat singularities and very short distances as invitations to new descriptions, rather than as places where infinity has been measured. The possibility that a complete theory of quantum gravity will render all physically relevant degrees of freedom finite in any finite region, and perhaps even cap the range of scales meaningfully defined, is very much alive. Potential infinity will remain as a method, even if actual infinity recedes as a fact. Could infinity be an illusion created by limited perspective? In a sense, yes. Many apparent infinities dissolve when we bring the right perspective to bear. A divergent energy becomes a finite shift after we redefine observable parameters. A singularity that looks like a hard edge reveals itself as a coordinate artifact when we choose better variables, or as a boundary of a theory's scope when quantum effects are included. A claim of infinite repetition of histories across space becomes, on inspection, a conditional statement that depends on both global geometry and the finiteness of local state spaces. In another sense, no, the concept of infinity does genuine explanatory work, and the ability to take limits is not a flaw in our thinking, but a strength. The illusion, if there is one, is not that we invented infinity, it is that we sometimes forget which of its roles we are playing. Mathematician proving theorems about completed structures, or physicist using idealizations to model a world where instruments and horizons are finite. What remains, after the arguments and counter-arguments, is a pragmatic map. Use the continuum where it delivers and track the domain of its legitimacy. Read divergences as messages about scale and method. Treat global claims about the world, spatial infinity, eternal time, unbounded multiplicity, with the respect due to hypotheses that outstrip direct test and anchor them to the local, statistical checks that we can perform. Keep an eye on hints from black hole thermodynamics and holography that degrees of freedom in a region are bounded, and keep searching for the theory that makes those hints precise. Refuse the easy comfort of declaring infinity merely imaginary or crudely real, and instead let its two faces, problem and tool, do their work. If infinity is real, it is not because we can hold it, but because the world refuses to finish. If it is not, our methods have still learned to speak as if it were and to be right. In either case, the horizon of understanding keeps its distance, and walking toward it is how thought becomes at home in a universe larger than certainty. Chapter 10. Living with Infinity, the Human Side. The word infinity touches nerves that other scientific terms do not. It belongs as easily to a physics lecture as to a lullaby, as at home in a proof as in a prayer. When people say they cannot wrap their minds around it, they are reporting something about cognition rather than confessing a failure of will. The human brain is built to predict near futures from recent pasts, to compress vast sensory streams into a limited set of actionable patterns, to prefer bounded tasks with attainable completions. Infinity resists all three habits. It opens the time horizon beyond the arc on which memory guides expectation. It refuses to be compressed into a digestible image. It offers tasks, explanation, improvement, curiosity, for which the notion of done is a mirage. The tension between machinery tuned for finitude and unbounded ideas is the source of both comfort and fear. Psychology has a vocabulary for this double pull. Awe is a blend of perceptual vastness and the need to update mental frameworks. It stretches models and shrinks the self just enough to make room for revision. People report awe in front of cliffs, cathedrals, mathematics, and newborns. The common thread is scale, spatial, temporal, or conceptual, jumping beyond the familiar. In experimental settings, awe is associated with broadened attention, a sense that time has slowed, and an increased willingness to explore. Yet awe shades easily into anxiety when prediction fails too fast. The very processes that make perception efficient, filtering, foregrounding, simplification, are strained by the unbounded, and the strain feels like dizziness. Infinity is therefore not just an idea to believe or reject. It is an experience to manage. Philosophers long ago recognized the stakes and gave them names. Arguments about infinity are often arguments about the limits of reason. The claim that there is no last number or that space has no edge is easy to state and hard to inhabit. Some thinkers found solace in a God whose perfection meant the absence of limits, treating infinity as a mark of the ultimate. Others cautioned that attributing boundlessness to human concepts risks contradiction, and that infinity used carelessly is a solvent that dissolves distinctions until thought cannot grip. Between these poles lies a disciplined middle ground. Treat the infinite as a structure that needs rules. That is why even very old debates return to exact distinctions between potential infinity, a process that can always be extended, and actual infinity, a completed totality. The distinction is not a mere scholastic trimming. It is a cognitive life raft. It keeps the mind from confusing the feeling that something could go on with the claim that it already exists completed. Artists and poets approach the oscillation without equations and sometimes with greater precision. When a line of verse turns on repetition with variation, or when a motif returns in a new key, the listener feels a promise of continuation that could, in principle, go on. Musical minimalism stacks loops whose interference patterns never quite settle. A fugue explores a theme as if it were a corridor with mirrors, planting another reflection just beyond reach. Visual artists play with tessellations and spirals that suggest unending extension inside a finite frame. The point is not to preach about infinity, but to let the audience feel the edge where pattern refuses closure and yet remains comprehensible. Good art makes that edge hospitable. It creates the sensation of inexhaustibility without the fatigue of formlessness. Language itself hides an engine suited for the unbounded. Human grammars allow recursion. A clause can contain a clause, a story can contain a remembered story, a promise can include the promise of future promises. Children discover this not by learning that infinity exists, but by playing with nesting structures until laughter reveals where attention falters. The fact that sentences can, in principle, be extended without bound is not a trick. It is one reason culture accumulates. Ideas can be refined indefinitely because language does not cap the number of distinctions we can draw. The unending is present not as an object but as a capacity for revision and extension. Daily life is threaded with softer infinities. The sun rises again, seasons return, debts accrue, and interest accrues on interest. Habits lay down grooves that invite more of the same, and attention feeds what it is given. Anyone who has scrolled a bottomless feed has felt a modern form of potential infinity, designed to keep you in the loop by refusing to provide a natural end. The design works because brains are tuned to hunt for closure. When closure is withheld at just the right rate, curiosity persists. This is the familiar mechanics of the compelling book or game, sharpened by industrial feedback and delivered to the palm. The lesson is not only caution about design. It is an opportunity to notice how easily the mind substitutes a promise of endless nexts for genuine amplitude in the present. The family and the city are also places where the infinite appears. A newborn makes time feel longer because futures multiply in imagination. But the daily work of care splinters time into many small tasks that never terminate once and for all. Grief returns under new lights and at new times, as if the mind were revisiting a coastline with changing tides. Communities build institutions, schools, archives, rituals, precisely because memory is more than a list of facts, and because meaning is not contained in a single event. What we call tradition is a managed infinity, a channel into which repetition can flow without flooding everything else. Because infinity touches meaning, religions treat it with care, and ordinary people inherit those treatments whether or not they know the theology behind them. For some traditions, eternity means endless time. For others, it names a timeless presence in which all times are present. Either way, the point is to mark what exceeds finite grasp and to place life in relation to it. Practices of prayer and meditation cultivate a posture toward the unbounded that is different from the scientist's posture, but not necessarily opposed to it. A scientist wants to measure and compare. A contemplative wants to receive and endure. Both are disciplined responses to immensity. Both require limits in order to sustain contact. A laboratory protocol here, a liturgy there. To live with infinity without drifting into vagueness, one needs anchors. Science supplies some. It teaches that when infinities appear in equations, one should ask what question was posed, which scale is relevant, and whether a different description will remove the divergence. That attitude translates outside the laboratory. If a task feels endless, change the question or change the timescale. Or pick a representation in which a small piece becomes tractable. Writing a book becomes finishing a page. Finishing a page becomes drafting a paragraph. Drafting a paragraph becomes choosing a starting sentence. What matters is that the representation preserves the structure of the work while making progress visible. Potential infinity is then not a trap, but a resource. There's always another small step to take. The same translation works in the arts. A canvas is finite, so is a performance. The trick is to create the experience of an inexhaustible interior within that finitude. A recording of a string quartet lasts an hour and can be replayed, and yet it can support a lifetime of listening, because the mind, not the disc, is the locus of the unending. Attention can be refined indefinitely, noticing new balances and conflicts, hearing a transition in fresh relation to what came before and after. This is not mystical inflation of the commonplace. It is a sober account of how perceptual and conceptual resources expand the object under scrutiny. The work remains bounded. The experience it affords is not. Boundaries are not the enemy of the infinite. They are the conditions under which it can be approached without harm. Every craft worker knows that constraints are productive. A poetic form is not a cage but a focusing lens. By choosing a meter or a scheme of repetition, the poet forces invention into a channel where echoes and variations can be richly perceived. Mathematicians choose axioms not because the world comes labeled with them, but because the right boundaries make exploration crisp and cumulative. In ordinary life, a budget, a schedule, and a promise serve the same role. They are not wishes for a smaller world. They are tools for turning the world's largeness into work one can do. Cognitive science adds a technical gloss. Working memory is limited. Attention is a bottleneck. The brain trades precision against cost. Under that accounting, the infinite is metabolized as a family of approximations. You never hold a complete map of a city at once. You hold a schema that can be queried for detail. You never hold the whole past or future. You hold narratives that can be edited. The power of thought comes not from storing a world, but from representing it at just the scales that matter for the present task. Infinity then is not a content, but a method. Unbounded refinement of representation when needed, refusal of unnecessary detail when not. Education offers a concrete example of how small steps build tolerance for endlessness. Students first learn that a limit exists by computing it in a simple case. Later, they learn the precise definition. Later still, they see why that precision matters in proofs and in computations that depend on it. Each stage uses a bounded exercise to point at an unbounded horizon. Moral education shows the same pattern. A child learns a rule, then an exception, then the reason that holds both. As the circle widens, the rule does not collapse into cynicism, and the exception does not expand into license. The infinite here is not quantity, but openness. There is always a further reason to consider, a larger context to consult. Modern life, for all its conveniences, magnifies encounters with the unbounded in ways that sometimes feel like pathology. The stream of information never stops. Causes to care about never run out. Work can become a game of asymptote chasing, where productivity approaches a ceiling while expectations climb. The rhetoric of infinite potential is as likely to exhaust as to inspire. A humane response borrows again from good science and good art. Choose variables that matter, track them honestly, and accept trade-offs. You cannot optimize all goals at once. The right aim is a trajectory that can be sustained, not a perfection that exists only as a boundary value. The humanities add calibration by showing how themes of limit and boundlessness appear in lives. Literature uses motifs of cycle and return not to deny change, but to give it structure. Myths of recurrence ask whether repetition erases meaning or exposes it. Dramas about ambition take seriously the question of whether desire knows a terminus. Satire reminds us that endless novelty can hide endless sameness, and that without criteria the new is indistinguishable from the noisy. Even comedy, with its running gags and callbacks, teaches an appetite for return that is satisfied by timing rather than by accumulation. What is at stake is not taste. It is the training of attention to recognize when more is more, and when more is merely more. Ethics must also reckon with the pull of the infinite. If obligations extended without end, would that make them meaningless or absolute? The language of human rights is deliberately unqualified. It claims universality as a moral infinity. Environmental stewardship speaks in horizons longer than any one life. Responsibility is cast as a chain through time that ought not be broken. Justice yearns for finality, yet remedial work often involves processes that cannot be declared done once and for all. Restoration, reconciliation, repair. The art is to combine strong commitments with practical stopping rules. An apology must be said, a promise must be kept, a harm must be made as right as possible within limits that are faced squarely rather than denied. Technology places the paradox in the palm. Algorithms can generate unending sequences of images or melodies. Simulations can run as long as power is supplied. Yet all of this content is produced from finite rules, and the success of compression algorithms depends on regularities that stop short of full randomness. There is a lesson here that scales beyond gadgets. Much of what looks infinite is a finite dynamic that, when iterated, throws off more pattern than we can catalog. Recognizing this is protective. It trains suspicion toward spectacles that promise infinity when what they deliver is merely length, and it frees admiration for works that create inexhaustibility from restraint. There is also a personal tact to ending well in a world that does not end. Because tasks and feeds and ambitions can always extend, people must practice the art of sufficiency, deciding that this painting is complete, that this experiment has yielded enough for a paper, that this conversation has reached rest. The art is not resignation. It is realism tuned to the fact that value arises in finite frames. The novel that implies a larger world is not improved by being twice as long. The symphony that ends with silence is not stingy but exact. Sufficiency is how finite agents keep faith with infinite aspiration. Education for this art may be the most practical gift a culture can give. It begins in small rituals that forbid the false infinite. A class ends on time. A meeting has an agenda and a decision. A family dinner includes a moment of gratitude that frames the day's unfinishable projects. These practices are not nostalgic discipline for its own sake. They are structures that let people meet the unbounded without becoming disoriented. They are civic equivalents of boundary conditions and equations, constraints that keep solutions stable. The sciences model the same dance. A research program accepts that there will always be more to measure and more to compute. It also accepts that experiments must end and papers must be submitted. Peer review and replication stitch finite contributions into a fabric that, taken together across time, approaches the inexhaustible. The pride of a result sits alongside the humility of knowing it will be extended or corrected. In this way, the laboratory becomes a school for living with infinity. It trains patience, it honors partial insight, and it treats progress as a curve that is meaningful long before it meets a limit. Thinking about mortality in the light of infinity rearranges emphasis. The thought that life is finite can make each day glow. The thought that time is endless can make the same day feel small. Both can be true. Finitude gives urgency and shape. Infinity gives scale and context. We do not need to live forever to touch the unbounded. We participate in it whenever we deepen attention, widen care, or pass a craft along. Even in love, the paradox holds. Promises use infinite language, always, forever, not because anyone can check them across eternity, but because the words name a posture rather than a schedule. The content of the vow is fidelity in the next hour and the next, not possession of the whole future. Romantic hyperbole is easy to mock, but the instinct is sound. When we love, we want to anchor a changing world with a constant. The anchor is not literally unbreakable, it is renewed. The willingness to renew is how finite creatures keep their promises in time. Infinity is not only out there in the distances or down there in the grains, it is in the way understanding unfolds. You will never be done learning, and that is not a failure. You will never be done repairing, and that is not futility. You will never be done wondering, and that is the point. The comfort and the terror are both part of the same revelation. Existence exceeds us, not as an enemy, but as a horizon. The sky you see tonight is not infinite for your eyes, but the questions it raises have no last step. Let that be an invitation rather than a threat, and let your finite days be the way infinity becomes gentle. We've drifted through the wide country of the infinite and made it back with a little more wonder in our pockets. If you're still awake and curious, there's another video waiting to carry you a bit farther down the river of ideas. If sleep has found you, let it. Good night, friend. Sweet dreams among the stars.